Welcome to the deep dive. You know we love a challenge, right? And, well, you've definitely sent us one this time.
Definitely a brain teaser.
You sent us some research on something called a non-homogeneous generalization of Berger's equations. And let me tell you, this is not your average light reading.
No.
So we were going to break it down and explore this intricate math and see how it connects to some pretty mind-blowing concepts like black holes and the very fabric of space-time.
Yeah. What's really cool about this paper by Francesco Maltese is how he takes the Berger's equation, which is, relatively simple, and pushes it to its limits, revealing its hidden potential to describe these complex phenomena in some unexpected settings.
Okay, so let's start by grounding ourselves.
Sure.
For those of us who might not be fluent in, the language of fluid dynamics, can you give us a quick rundown of what the Berger's equation is and what it's traditionally used for?
Okay, so imagine watching a river flow, right? With all its twists and turns, rapids, and calm stretches. The Berger's equation, in its classic form, helps us understand how that flow behaves, factoring in things like the water's viscosity, basically its resistance to flow, and any external forces acting on it, like gravity or wind.
So it's a way to mathematically represent how fluids move and change under different conditions?
Precisely. Now, what Maltese does in this paper is take this equation and supercharge it.
Okay.
Replacing standard derivatives with these more abstract mathematical operators.
Okay.
And these operators act like powerful instructions dictating how a function changes and behaves.
Okay, so we're stepping into a more abstract world, moving beyond the physical realm of water and wind.
Yeah.
I'm intrigued, but I have to admit, my brain is already doing a bit of a mental stretch here.
That's where the real excitement begins.
Okay.
This leap into abstraction unlocks the equation's power to describe phenomena far beyond its traditional domain.
Okay.
It allows us to incorporate things like fractional derivatives, which can describe changes that unfold in more nuanced ways, even over fractional amounts of time.
Fractional time. Now that sounds like something straight out of a science fiction novel.
Well, it's not quite time travel.
Okay.
But fractional derivatives do give us a way to model situations where changes happen in a less straightforward manner than traditional derivatives can capture. It's like having a finer-grained lens for observing how things evolve.
Got it. So we're equipping the Berger's equation with some serious mathematical firepower.
Yes.
But I'm still a bit puzzled about how hyperbolic space enters the picture.
Okay.
It sounds a bit like something out of a Salvador Dali painting, to be honest.
Okay, think of it this way.
Right.
We're used to living in this flat Euclidean world where parallel lines never meet, and the angles of a triangle always add up to 180 degrees.
Right.
But hyperbolic space throws those familiar rules out the window.
Oh.
It's a curved, non-Euclidean geometry where parallel lines diverge and the angles of a triangle add up to less than 180 degrees.
Okay, I'm starting to get a visual, but how does this mind-bending geometry connect to the generalized Berger's equation?
This is where it gets really cool. The paper shows us how the generalized Berger's equation with its souped-up operators can be used to understand the behavior of particles in hyperbolic space.
Okay.
Specifically, it connects to something called Brownian motion, which is that random jiggling of particles due to constant collisions with their neighbors.
So we're using this amped-up Berger's equation to model the seemingly chaotic dance of particles in this warped non-Euclidean space.
Yeah.
Okay. That's pretty wild.
It is, and what's even more surprising is that despite all this added complexity, Maltese actually presents methods for finding exact solutions to this generalized Berger's equation in these exotic settings.
Wait, hold on.
Yeah.
Exact solutions.
Yeah.
You're telling me we can solve this equation with all its abstract operators and hyperbolic twists and get a precise answer?
Yeah.
That seems almost too good to be true.
It does seem a bit magical, right?
Yeah.
But Maltese achieves this through some very clever mathematical maneuvering.
Okay.
He introduces these ingenious transformations, including one that involves Hermite polynomials, which are a special family of functions often used in physics and probability.
So he's basically finding ways to rewrite the equation in a form that we can solve using these known mathematical tools like the Hermite polynomials.
Exactly.
It's like finding a secret passageway through a mathematical labyrinth.
It is. It's a testament to the power of mathematical ingenuity.
Yeah.
To unlock these hidden connections and find order within this seeming chaos. And believe it or not, we're just getting started. The paper takes us even further down the rabbit hole. Exploring how the generalized Berger's equation can be applied to understanding phenomena in Schwarzschild spacetime.
Okay, now we're talking black holes.
Yes.
Schwarzschild spacetime is the spacetime geometry around a non-rotating uncharged black hole, right?
That's right.
A place where gravity is so strong that even light can't escape.
Exactly. It's a region where our everyday intuition about space and time completely breaks down. And yet Maltese shows us that the generalized Burger's equation with its abstract operators can be used to describe certain events occurring within this extreme environment.
Okay, my head is officially spinning.
Yeah.
We've gone from modeling river flows to unraveling the mysteries of black holes. But wait, there's more, isn't there?
There is.
Something about Ricci solitons.
You gotta think of Ricci solitons as special solutions
Okay.
to a kind of geometric evolution equation. Like watching a shape change over time, but it always retains a certain self-similarity.
Okay.
Kind of like a fractal pattern.
So even though the shape is evolving,
Okay.
it keeps a certain underlying structure.
Precisely. And Maltese demonstrates how the generalized Burger's equation can provide insights into the behavior of these Ricci solitons, showcasing its incredible versatility.
Okay, I need a moment to catch my breath.
Yeah.
We've covered so much ground, and it's clear we're only scratching the surface here.
Yeah.
So to recap, we started with the Burger's equation, which traditionally describes fluid flow. Maltese then generalized this equation by introducing these more abstract operators,
Right.
giving it superpowers to tackle problems in hyperbolic space,
Yeah.
Schwarzschild spacetime, and even on Ricci solitons.
Yeah.
Am I on the right track?
Absolutely. You've grasped the essence of what we've explored so far.
Okay.
We've seen how a seemingly simple equation, when generalized and transformed, can become this powerful tool for understanding a wide range of complex phenomena.
It's incredible to see how math can provide such a unifying framework for exploring the universe.
Yeah.
But let's dive a little bit deeper into the specifics here.
Okay.
How does Maltese actually find solutions to this generalized Burger's equation? What are the tricks of the trade, so to speak?
Well, he presents two main methods.
Okay.
The first involves transforming solutions of simpler linear equations into solutions for the more complex generalized Burger's equation. It's like building a bridge between the familiar and the unknown, using what we already know to unlock this new territory.
Okay, that sounds like a clever strategy.
Yeah.
But I imagine there are some ground rules involved, right?
Absolutely, to ensure that transformation process is mathematically sound.
Yeah.
Maltese sets specific conditions on the operators involved.
Okay.
For example, he requires them to obey the Leibniz property, which governs how an operator acts on the product of two functions.
Okay.
Think of it as a set of rules that guarantee the mathematical integrity of the transformation.
So it's like making sure we're following the proper grammar of mathematics.
Exactly. Now, in one specific scenario where the spatial operators are equal, and a particular linear operator L is the identity operator, Maltese introduces a special tool, generalized Hermite polynomials, to find solutions.
Hermite polynomials. I vaguely remember those from my math classes.
Yeah.
But what makes them generalized in this context?
Well, traditionally, Hermite polynomials are defined using standard derivatives.
Right.
But in this case, Maltese adapts them to work with the more abstract framework of the generalized equation, replacing those standard derivatives with the more general operators we've been discussing.
So he's upgrading these polynomials to fit the more powerful tools he's using.
Exactly.
But how do they actually help us find solutions?
It's a multi-step process.
Okay.
First, we need to find a solution to a related heat type equation, which describes how heat diffuses over time. If the initial condition for that solution is a generalized Hermite polynomial, then we can apply a specific transformation to get a solution to the generalized Burger's equation.
So it's like a chain reaction where the solution to one equation paves the way for the solution to the other. But what happens when the linear operator L isn't the identity operator? Does the method still work?
It does. The method can still be applied, but the specifics of the transformation process will change. Maltese provides an example in the hyperbolic Poincare half-plane, which is a model of hyperbolic space often used in geometry, where L is not the identity operator.
Okay, so even with a more complex L, we can still find solutions using this transformation technique.
Yes.
But I have to admit, all this talk about operators and transformations can get a bit abstract.
Yeah.
Did you give us a concrete example of how this method plays out in practice?
Absolutely. Let's delve into example 3 from the paper.
Okay.
In this example, Maltese considers the generalized Burger's equation in the hyperbolic Poincare half-plane, choosing specific operators and a particular form for L.
Okay.
He then demonstrates how to find a solution using the transformation method we've been discussing.
Okay, so we're getting down to the nitty-gritty.
Yeah.
Can you walk us through the steps?
He begins by establishing a connection between the generalized Burger's equation and Brownian motion in the hyperbolic Poincare half-plane.
Okay.
Remember, Brownian motion is that random jiggling of particles due to collisions.
Right. That dance of chaos. But how does it tie into the Burger's equation?
Well, in its original form, the Burger's equation describes fluid flow. Now, imagine a fluid made up of tiny particles undergoing Brownian motion.
Okay.
The generalized Burger's equation in this case can be used to describe how this fluid behaves in the curved space of the hyperbolic Poincare half-plane.
So we're essentially using this souped-up equation to understand the collective motion of particles that are individually moving randomly. It's like finding order within chaos.
It is.
But how does Maltese find the solution?
He starts with the equation describing Brownian motion on a hyperbolic half-plane,
Okay.
which involves a special operator called the hyperbolic Laplacian. He then applies a carefully chosen transformation to this equation using an exponential function.
So he's using this exponential function to bridge the gap between the Brownian motion equation and the generalized Burger's equation.
Exactly. And the beauty of it is that the solution to the Brownian motion equation is already known.
Okay.
So by applying the transformation, Maltese cleverly obtains a solution to the generalized Burger's equation expressed in terms of this known solution.
It's like a mathematical puzzle where the pieces perfectly fit together. But I noticed a cautionary note in the paper about the domain of the solution. Something about logarithms.
You're right. The solution involves a logarithmic function,
Yeah.
which is only defined for positive values.
Right.
This means we have to be mindful of the regions in the hyperbolic Poincare half-plane where the solution is actually valid.
Okay, so we can't just blindly apply the solution everywhere.
Right.
We have to consider the mathematical and physical constraints. It's a reminder that even with elegant mathematical techniques, we need to stay grounded in reality.
Yeah.
I believe Maltese presents a second method for finding solutions right.
You're right. Let's talk about invariant subspaces.
Okay, that sounds intriguing. Can you explain what those are?
Imagine a mathematical space filled with functions,
Okay.
kind of like a library filled with books.
Uh-huh.
An invariant subspace is a special section of this library where the functions have a unique property. They remain unchanged even when certain mathematical operations are applied to them.
So it's like a protected zone within this mathematical library.
Exactly. And the brilliant thing is that if we can find these invariant subspaces, the generalized Burger's equation simplifies considerably when restricted to them.
Okay.
This makes finding solutions much easier.
So we're strategically narrowing down our search space by focusing on these special regions where the equation becomes more manageable.
Precisely.
But how do we actually find these invariant subspaces in the first place?
Maltese provides a set of conditions that help us identify these special spaces.
Okay.
These conditions involve the operators we've been discussing, ensuring certain properties hold true for the functions within these subspaces, making them suitable for finding solutions.
It's like a treasure map guiding us towards the hidden gems within this vast mathematical landscape.
Yeah.
But I learned Beth through examples.
Sure.
Can you walk us through one?
Absolutely. Let's look at example 4. In this example, Maltese considers a specific version of the generalized Burger's equation with a fractional time derivative and particular choices for the other operators.
Okay.
He then identifies an invariant subspace generated by the functions 1 and x.
Okay.
Let's call it W.
Okay.
Now, because this subspace is invariant, Maltese can make an educated guess about the form of the solution.
Okay.
He assumes it will have the structure uxt equals b1t x plus b0t, where b1t and b0t are unknown functions of time.
So we're assuming the solution will be a linear function of x with coefficients that depend on time.
Precisely. And the next step is to determine those time-dependent coefficients.
Okay.
By plugging this assumed solution into the generalized Burger's equation and using the properties of the invariant subspace, Maltese derives a system of differential equations for b1t and b0t.
Okay.
Solving the system reveals the explicit form of these coefficients, leading to the solution of the generalized Burger's equation.
So it's like solving a jigsaw puzzle. We start with a framework based on the invariant subspace, then fill in the missing pieces by solving the differential equation.
Exactly.
But what do the solutions actually look like in this case?
In this example, the coefficients are expressed in terms of a special function called the Mittag-Leffler function,
Okay.
which often pops up when dealing with fractional derivatives.
The Mittag-Leffler function seems to be a recurring character in this story.
It is. It's a powerful mathematical tool for handling the complexities of fractional derivatives.
Okay.
But we're just scratching the surface here. Maltese goes on to apply the invariant subspace method to even more mind-boggling scenarios, including the hyperbolic Poincare half-plane and even Schwarzschild spacetime.
Okay, I'm ready for the next level. This deep dive is turning out to be quite the adventure. But I think we've covered enough ground for now.
You're right. We've certainly given our listeners a lot to digest.
We've laid the groundwork, explore the two main methods for finding solutions, the transformation method and the invariant subspace method, and even delved into some specific examples.
We have.
But the journey's not over yet.
Right.
In the next part of our deep dive, we'll explore how Maltese applies these methods to the truly mind-bending realms of black holes and Ricci solitons.
Right.
So stay tuned for more mathematical marvels.
Yeah. Welcome back to the deep dive. Let's pick up where we left off exploring this fascinating world of generalized Burger's equations.
Okay.
Last time we talked about two main methods Maltese uses to find solutions.
Right.
The transformation method and the invariant subspace method. Now let's see these methods in action by taking a closer look at some specific examples.
Okay. I'm excited to see how these abstract concepts translate into real-world applications. I'm particularly curious about how these methods work in the context of hyperbolic geometry.
A great place to start is with example 1, where Maltese tackles the generalized Burger's equation in the hyperbolic Poincare half-plane, a model of hyperbolic space.
Okay.
It's a space where the usual rules of geometry don't quite apply. Parallel lines diverge, and the angles of a triangle add up to less than 180 degrees.
Right.
Imagine trying to navigate with a map that constantly changes its scale.
Yeah.
That's hyperbolic space for you.
Okay, my brain is already bending. So how does Maltese apply his methods in this warped space?
He uses the transformation method we discussed earlier, relating solutions of the generalized Burger's equation to those of a simpler linear equation. The key to this transformation is finding the right function.
Okay.
Let's call it g.
Okay.
That acts as a bridge between the two equations.
That magical function g that helps us unlock the secrets of the more complex equation.
Exactly. In this example, Maltese chooses an exponential function for g.
Okay.
This function satisfies the necessary mathematical conditions to ensure that the transformation process is valid.
So by using this exponential transformation, Maltese can cleverly leverage solutions from a simpler equation to find solutions for the generalized Burger's equation in this mind-bending hyperbolic space.
Yeah.
But what does that simpler equation look like?
It's a heat-type equation that describes how something represented by a function diffuses or spreads out over time in the hyperbolic Poincare half-plane.
Okay.
Imagine heat flowing across the surface of a saddle. That gives you a sense of how this equation behaves in curved space.
Okay, I'm starting to see the connection. So we're using an analogy of heat flow to understand how this mathematical function evolves in hyperbolic space.
Yes.
But how do we link the solutions of this heat-type equation to the solutions of the generalized Burger's equation?
Maltese introduces another transformation.
Okay.
Represented by the Greek letter.
Okay.
This transformation connects the solution of the heat-type equation to the solution of the generalized Burger's equation. It also involves a function of time that must satisfy a specific condition related to its derivative.
So there's a precise mathematical link between the solutions of the two equations governed by this time-dependent function.
Yes.
But what do the actual solutions look like? Do they have a recognizable form?
This is where those special functions we talked about earlier come in the generalized Hermite polynomials.
Okay.
Maltese shows that if we have a solution to the heat-type equation, and if the initial condition for that solution is a generalized Hermite polynomial, then we can use the transformation we just discussed to get a solution to the generalized Burger's equation.
So the generalized Hermite polynomials act like seeds, providing the starting point for generating solutions to the more complex equation. It's like planting a specific type of mathematical seed in the right soil to grow a particular kind of solution.
That's a great analogy. And in this example, the final solution to the generalized Burger's equation is expressed in terms of these generalized Hermite polynomials, reflecting the initial conditions and the unique characteristics of the hyperbolic Poincare half-plane.
So the solutions have a specific structure that depends on those initial conditions and the geometry of the space we're working in.
Yes.
But Maltese doesn't stop there, does he? He provides another example in the hyperbolic Poincare half-plane. Example 2, where he slightly tweaks the operators involved.
Exactly. He demonstrates how adaptable his method is by exploring what happens when we use slightly different operators, essentially changing the rules of the mathematical game.
Okay.
In this case, he modifies one of the operators by dividing it by a hyperbolic sine function,
Okay.
which subtly changes how it affects the functions we're dealing with.
It's like changing the settings on a powerful mathematical machine.
That's a great way to think about it. And despite this change, Maltese shows that the solution process follows a similar pattern as in the previous example.
Okay.
He again uses the transformation method with the same exponential function for g.
So the same exponential transformation still works its magic, even with the adjusted settings.
Yes.
But what about the solution itself? Does it still involve those generalized Hermite polynomials?
It does. The solution maintains a similar form, but the argument within the generalized Hermite polynomial is slightly different, reflecting the change in the operators.
So the details of the solution are sensitive to the specific choice of operators, but the overall structure and reliance on generalized Hermite polynomials remain consistent.
Yes.
It's fascinating how changing the rules of the game can lead to subtle but important variations in the outcome. But let's shift gears and dive deeper into the second method, the invariant subspace method.
Excellent idea. Remember, this method involves finding special spaces of functions,
Yeah.
invariant subspaces,
Yes.
that remain unchanged under the action of the operators involved.
Right.
It's like finding those books in the mathematical library that are immune to any rearrangement scheme.
Right, those books that always stay in the same spot no matter how many times the library is reorganized.
Right.
But how do we identify these mathematical safe havens?
Maltese provides us with a set of conditions denoted as H3.1 that involve the operators NDXD, MDXD, and LD.
Right.
These conditions act like a checklist, ensuring that the functions within these subspaces possess certain properties that make them ideal for finding solutions.
So it's like having a key that unlocks the door to these hidden mathematical realms. But I always find it helpful to see how things work in practice.
Sure.
Can you walk us through a specific example?
Absolutely. Let's revisit example 4.
Okay.
Where Maltese tackles a generalized Burger's equation that includes a fractional time derivative, a concept we touched upon earlier.
Right.
He chooses specific forms for the operators setting NDXD and MDXD to the partial derivative with respect to x and LD to the identity operator.
Okay, so we're working with a specific set of rules and operators.
Yeah.
But how does Maltese find the invariant subspace in this case?
He demonstrates that the space generated by the functions 1 and x, let's call it W, meets the criteria for being an invariant subspace. This means that any linear combination of 1 and x, like 2 plus 5x or minus 1 plus 3x, remains unchanged under the action of the operator.
So W is like a fortress protecting its mathematical inhabitants from the transforming power of the operators. But how does this help us solve the equation?
Because W is an invariant subspace, Maltese can strategically search for solutions that have a specific form. He assumes the solution will look like a linear function of x, but with coefficients that depend on time.
So it's a linear function with a time twist.
Exactly. He assumes the solution will have the form uxt equals b1tx plus b0t, where b1t and b0t are unknown functions of time. Then by substituting this assumed solution into the generalized Burger's equation and using the properties of the invariant subspace, he derives a system of differential equations for these unknown functions.
It's like reverse engineering the solution.
Yeah.
We start with a guess based on the structure of the invariant subspace, then work backward to figure out the missing pieces.
You've got it. And by solving these differential equations, we find the explicit form of b1t and b0t, which ultimately gives us the solution to the generalized Burger's equation.
So it's a step-by-step process guided by the properties of the invariant subspace that leads us to the solution. But what do those solutions look like in this case?
In this example, the solutions are expressed in terms of that special function we've encountered before, the Mittag-Leffler function.
The Mittag-Leffler function strikes again. It seems to be indispensable when dealing with fractional derivatives.
It is. It's a powerful mathematical tool that helps us tame the complexities of those fractional time derivatives. But to show the versatility of the invariant subspace method, Maltese doesn't stop there. He provides another example. Example 5, set in the hyperbolic Poincare half-plane.
Okay.
This time he chooses different operators that incorporate the hyperbolic sine function, reflecting the curvature of the space.
So we're back to hyperbolic geometry, but with a twist.
Exactly. And in this example, the invariant subspace is generated by slightly different functions.
Okay.
The natural logarithm of the hyperbolic tangent of point 2 and the constant function 1.
Okay.
These functions capture the unique features of the hyperbolic Poincare half-plane.
So the invariant subspace reflects the geometry of the space we're working in, just like in the previous example.
Exactly. And despite the change in operators in the different invariant subspace, the solution process remains structurally similar.
Okay.
We assume a solution based on the invariant subspace, substitute it into the equation, derive a system of differential equations, and solve for the unknown coefficients. And once again, the solutions are expressed in terms of the Mittag-Leffler function.
It's like a familiar dance with slightly different steps. But Maltese makes an interesting observation in remark 3.2, doesn't he? Something about the robustness of the invariant subspace method.
You're right. He points out that even if we tweak one of the operators, specifically the one related to the hyperbolic sine function, the invariant subspace and the solutions remain the same. This highlights the remarkable resilience of this method.
So even if we change the rules of the game slightly, as long as we stay within the boundaries of the invariant subspace, the solutions hold firm. It's a testament to the power and flexibility of this technique.
Indeed. It shows us that even in the face of complexity and variation, there are underlying mathematical structures that guide us towards solutions.
This deep dive is turning out to be an incredible journey. We've gone from the basics of the Burger's equation to exploring its generalization in hyperbolic space. And now we've seen two powerful methods for finding solutions, illustrated with concrete examples.
Yeah, we've uncovered the beauty of mathematical transformations,
Yeah.
the elegance of invariant subspaces, and the recurring role of the Mittag-Leffler function in tackling fractional derivatives.
But the adventure isn't over yet. In the next part of our deep dive, we'll venture into even more mind-boggling territory.
Yes.
Exploring how Maltese applies these methods to the enigmatic realm of black holes and the dynamic world of Ricci solitons. So buckle up, because the best is yet to come.
Yeah. Welcome back to the deep dive. We've journeyed through the world of generalized Burger's equations, exploring its transformation from a simple model of fluid flow to a powerful tool for understanding these complex phenomena in curved spaces. Now, in this final part, we're going to take on the ultimate challenge.
Okay.
Applying these concepts to the most extreme environments imaginable, black holes and Ricci solitons.
I have to admit, I'm both excited and a little intimidated. These are some of the most mind-boggling concepts in physics, and to think we can explore them through the lens of mathematics is truly awe-inspiring.
Let's start with example 9, where Maltese dives headfirst into the depths of Schwarzschild spacetime.
Okay.
This is that warped spacetime geometry surrounding a non-rotating, uncharged black hole.
It's a region where gravity reigns supreme, distorting space and time in ways that defy our everyday experience.
Yeah. Black holes have always captured my imagination. They're like these cosmic enigmas shrouded in mystery.
Yeah.
But how do we even begin to describe such a bizarre and powerful gravitational environment using math? The key is the Schwarzschild metric, a mathematical blueprint that tells us how to measure distances and time intervals near a black hole.
Okay.
It's like a map that guides us through this warped landscape where the familiar rules of geometry no longer apply.
So it's a way to capture those distortions of space and time caused by the immense gravity of the black hole. It's like trying to navigate with a map that constantly stretches and shrinks around you.
Exactly. The Schwarzschild metric incorporates these key physical parameters like the mass of the black hole, the speed of light, and the distance from the black hole's center.
Right.
These parameters determine the extent to which space and time are warped.
It sounds like we're entering a realm where intuition goes out the window.
Yeah.
So how does Maltese incorporate this mind-bending metric into the generalized Burger's equation?
He utilizes the full hyperbolic Laplacian operator, a mathematical tool that captures how a function changes across this warped spacetime.
Okay.
This operator is expressed in terms of the Schwarzschild metric, allowing us to account for that unique curvature introduced by the black hole's immense gravity.
So we're upgrading our mathematical toolbox to operate within the extreme environment of Schwarzschild spacetime.
Yeah.
But what about those other operators we've been discussing, NDXD and NDXT? How do they fit into this picture?
Maltese carefully selects these operators to ensure they align with the conditions required for applying the invariant subspace method. He derives expressions for these operators in terms of the Schwarzschild metric components, ensuring they capture the unique features of this warped spacetime.
Okay, it's like fine-tuning our instruments to make sure they function properly in this extreme gravitational field.
Right, good.
But what about the linear operator LD? Does it play a specific role in this scenario?
In this case, LD is simply the identity operator.
Okay.
While this simplifies things somewhat, the real challenge lies in grappling with the complexity of the Schwarzschild metric and the hyperbolic Laplacian operator.
So we've traded one complexity for another. But how does Maltese manage to find an invariant subspace within this warped spacetime? It seems like finding a stable island in a sea of distortion.
It is a remarkable feat. Maltese identifies a subspace generated by specific functions of the coordinates TRAF, which represent time radial distance and angular positions in this spacetime.
Okay.
These functions involve logarithms, trigonometric functions, and constants related to the black hole's mass and the speed of light.
So the invariant subspace itself reflects the unique characteristics of Schwarzschild spacetime, incorporating those key physical parameters.
Yeah.
It's like finding a set of mathematical blueprints that are perfectly adapted to this warped environment.
Exactly.
But what about the solutions to the generalized Burger's equation? Do they reveal anything about the behavior of phenomena near a black hole?
The solution Maltese derives is truly remarkable. It incorporates those key features of the Schwarzschild metric, including the black hole's mass and the speed of light. The solution combines exponential functions, logarithms, trigonometric functions, and of course the Mittag-Leffler function reflecting that fractional time derivative.
It's like a mathematical symphony, with each element playing a specific role in capturing the essence of this extreme environment. But I recall that Maltese also provides a cautionary note about the solution's domain.
Yes.
Something about the limitations imposed by logarithms.
You're right. He reminds us that logarithms are only defined for positive values. This means we need to be mindful of the range of coordinates for which the solution is valid, taking into account the constraints imposed by the Schwarzschild metric itself.
So even within this mathematically elegant framework, we can't escape the boundaries of mathematical and physical reality. It's a reminder that even the most powerful theories must be grounded in the limitations of our universe. But let's shift our focus to the final application. Example 10, where Maltese explores the generalized Burger's equation on a Ricci soliton.
Excellent Ricci solitons are these fascinating geometric objects that evolve over time while maintaining a certain self-similarity.
Okay.
Kind of like a shape-shifting creature that always retains its fundamental form. Imagine a clay sculpture that morphs and flows,
Okay.
yet always preserves its essential features.
That's a captivating image. It makes these abstract mathematical objects feel a bit more tangible. But which specific Ricci soliton does Maltese choose to work with?
He selects the cigar soliton,
Oh.
a well-studied solution in geometric analysis. It gets its name from its cigar-like shape, which remains constant even as the soliton stretches and evolves over time. It's this dynamic yet self-similar geometric structure, a beautiful example of order within change.
So we're dealing with a geometric object that's constantly in motion, yet always retains its distinctive form. It's like a dance between stability and transformation.
Yeah.
How does Maltese incorporate this dynamic object into the framework of the generalized Burger's equation?
He introduces a metric that specifically describes the geometry of the cigar soliton. This metric involves the coordinates x, y, and time, and it captures how distances are measured on the evolving surface of the soliton. It's like having a tailor-made measuring tape that adapts to the soliton's changing shape.
So we're once again tailoring our mathematical tools to fit the unique features of the object we're studying. It's like we're crafting a custom-made lens to observe this evolving geometric wonder.
Precisely. Maltese then selects operators, ndxd and mdx, that are compatible with the cigar soliton's metric, ensuring they accurately reflect its unique geometry.
It's as if we're building a specialized toolkit, carefully choosing the right instruments to explore the intricate workings of this mathematical object. But what about the linear operator LD? Does it play a special role in this scenario?
As in the previous example with the black hole, LD is simply the identity operator.
Okay.
This choice simplifies the problem somewhat, but the real challenge lies in capturing that dynamic, self-similar nature of the cigar soliton within the solution process.
So we're faced with the task of finding solutions that not only satisfy the generalized Burger's equation, but also reflect that evolving nature of the cigar soliton. It's like trying to hit a moving target.
Exactly. But Maltese rises to the challenge, identifying an invariant subspace that reflects the key features of the cigar soliton's geometry.
Uh-huh.
This subspace is generated by the functions x, y, and 1, capturing the essence of the soliton's form as it evolves over time.
So the invariant subspace provides an anchor, a stable point of reference within this dynamic geometric landscape.
Yeah.
It's like having a fixed compass that guides us through the shifting terrain.
That's a great analogy. And with this invariant subspace as a guide, Maltese derives a solution that elegantly incorporates the key features of the cigar soliton's metric, including that exponential dependence on time and the specific combination of x and y coordinates that define its shape. And as we've come to expect, the solution once again features the Mittag-Leffler function, highlighting its remarkable versatility in solving equations with fractional time derivatives.
It's amazing how this single function, the Mittag-Leffler function, keeps popping up in such diverse contexts. It's like a mathematical chameleon adapting its form to fit the specific problem at hand.
It is a testament to the interconnectedness of mathematics, how a single concept can have such far-reaching applications.
This deep dive has taken us on an incredible journey, from that familiar world of fluid flow to the mind-bending realms of black holes and Ricci solitons. We've witnessed that power of mathematical generalization, the elegance of transformations in invariant subspaces, and the remarkable versatility of functions like the Mittag-Leffler function.
We've seen how these abstract mathematical concepts can be used to describe some of the most extreme and enigmatic phenomena in our universe, revealing hidden patterns and connections that might otherwise remain invisible.
It's been a truly mind-expanding experience, and it leaves me with a sense of awe and wonder knowing that there are still countless mathematical mysteries waiting to be explored, and that these explorations can lead us to a deeper understanding of the universe and our place within it.
Thank you for joining us on this deep dive into the world of generalized Burger's equations. We hope you've enjoyed the journey as much as we have.
Welcome to the deep dive. Today, we're going to untangle some seriously fascinating math.
Oh, yeah.
Get ready to explore the world of non-homogeneous generalizations of Burger's equations. Now, I know that sounds intimidating, but trust me, it's way cooler than it sounds.
It really is. The Burger's equation you see is a fundamental tool in fluid mechanics.
Okay.
Used to describe things like shock waves, and believe it or not, it can even model traffic flow.
So this math helps us understand how things move, from ocean waves to cars on the freeway.
Yeah.
That's pretty neat. But we're going deeper than the basic Burger's equation today. Right?
Exactly. We're diving into a research paper that takes the Burger's equation to a whole new level,
All right.
making it even more powerful and versatile.
Okay, I'm intrigued. What makes this research paper so special?
Well, it generalizes the Burger's equation in a couple of really important ways.
Okay.
First, instead of using standard derivatives, they replace them with more general operators. This gives the equation more flexibility to model different types of phenomena.
So it's like upgrading from a basic wrench to a multi-tool that can handle all sorts of situations.
That's a great analogy. And second, they expand the equation from one spatial dimension to multiple dimensions.
Wow.
Imagine going from a flat map to a 3D globe.
Okay.
It opens up a whole new world of possibilities.
Okay, I'm starting to see why this is a deep dive.
Yeah.
But before we get too far, let's make sure we're all on the same page. Can you remind us what the standard Burger's equation is all about?
Of course. In its simplest form, the Burger's equation is a partial differential equation that described how the velocity of a fluid changes over time and space. It's a way to capture the dynamics of things like waves and shocks.
So it's a mathematical tool for understanding how things flow and change. And this research paper takes that tool and makes it even more powerful by generalizing it.
Precisely. And that leads to some really amazing results. They show how to solve these generalized Burger's equations using some clever techniques.
Like what? I'm ready for some mathematical magic.
One trick they use is transforming solutions from simpler equations. It's like taking a blueprint for a simple house and modifying it to build a complex skyscraper.
Okay, that's a pretty cool trick. How does that work?
Essentially, they lay out very specific conditions under which solutions to a linear operator equation can be transformed into solutions for the non-homogeneous Burger's equation, which is much more complex. They use a function they call g to make this transformation possible.
So G is like a mathematical translator,
Yeah.
taking the solution from one equation and mapping it onto the more complex Burger's equation.
Exactly. It ensures that the solution fits perfectly within the framework of the generalized Burger's equation. Now, this paper dives into a fascinating subfamily of solutions related to Hermite polynomials.
Hermite polynomials. Now, those sound familiar. Weren't those named after some famous mathematician?
You're right. Charles Hermite was a French mathematician who made significant contributions to number theory,
What?
algebra, and analysis.
And these Hermite polynomials, they're not just some random mathematical objects, are they? They have real-world applications.
Absolutely. They pop up in various fields like probability,
Hmm.
physics, and even finance. Think of them as special functions with unique properties that make them incredibly useful for solving certain types of problems.
Okay, so these Hermite polynomials play a role in solving these generalized Burger's equations. But how exactly do they fit into the picture?
Well, the researchers found that in specific cases, these generalized Hermite polynomials actually arise as solutions to the equations.
Wow.
And what's really intriguing is the connection they found to the hyperbolic half-plane.
Hold on, hyperbolic half-plane. Now that sounds like something out of a science fiction novel. Can you break that down for us?
Imagine a world where parallel lines can meet. That's the essence of non-Euclidean geometry.
Hmm.
And the hyperbolic half-plane is a classic example of this strange and beautiful type of space.
Okay, my brain is doing a little gymnastics here. So we're talking about solving these equations, not just in our normal everyday space, but in this bizarre hyperbolic world.
Exactly. And these Hermite polynomials turn out to be incredibly useful for navigating this unusual terrain.
Wow. So they're like a mathematical compass that helps us find our way through this non-Euclidean jungle. That's pretty amazing.
It is. The researchers even give a concrete example of how to solve a generalized Burger's equation in the hyperbolic plane using these Hermite polynomials.
Why?
It's quite a feat.
Okay, my mind needs a moment to catch up with all these mind-bending concepts. But I'm eager to dive deeper. What other techniques do they explore in this paper?
Well, they also introduce another method for solving these equations.
Okay.
The method of invariant spaces.
Invariant spaces, if I recall correctly, it's about finding sets of functions that stay the same even when you apply certain transformations, right? Like a group of friends who always stick together no matter what adventure you throw at them.
That's a great way to put it. It's like having a group of mathematical objects that maintain their relationships to each other even when you rearrange them.
So how do these invariant spaces help in solving these complex equations?
The researchers show that by identifying the right invariant spaces, you can transform the generalized Burger's equation into a system of ordinary differential equations.
Okay.
And that's a huge advantage because ordinary differential equations are generally easier to solve than partial differential equations.
So it's like they're breaking down a complex puzzle into smaller, more manageable pieces.
Exactly. And that makes it easier to find the solutions we're looking for. Now, are you ready for something even more mind-boggling?
I think so.
They even introduced the concept of fractional derivatives.
Fractional derivatives. That sounds like something straight out of a science fiction movie.
It might sound futuristic, but it's a real and fascinating area of mathematics. You see, in calculus, we're used to taking derivatives which tell us the rate of change of a function. But what if we wanted to take half a derivative or a third of a derivative? That's where fractional derivatives come in.
Okay, now my brain is officially starting to melt. How can you possibly take a fraction of a derivative?
It's a bit tricky to explain without getting into the technical details, but essentially, fractional derivatives are a generalization of the derivative concept. It's like taking the idea of the derivative and making it even more powerful and flexible.
I'm trying to picture what that would look like, but it's like trying to imagine a fourth dimension. So they're using these fractional derivatives in the context of these generalized Burger's equations.
They are. And it turns out that fractional derivatives provide a new and powerful way to model and analyze these equations.
This deep dive is getting deeper by the minute. I have to admit, though, it's exhilarating to explore these uncharted mathematical waters.
Hold on tight, because now we're venturing into curved spacetimes. Think relativity, black holes, the fabric of the universe.
Okay, now you're speaking my language.
Yeah.
This is where the math meets the mysteries of the cosmos. I'm all ears.
To model the generalized Burger's equation in curved spacetimes, they use a key tool from differential geometry, the Laplace-Beltrami operator.
Differential geometry. That's the study of curves, surfaces, and how they behave in different spaces, right?
Yeah.
I'm starting to see a pattern here. They keep connecting this equation to all these other fascinating areas of mathematics.
You're absolutely right. They're weaving together different strands of mathematical thought to create a rich tapestry of understanding. And it leads to some truly remarkable results.
So where do these curved spacetimes and the Laplace-Beltrami operator take us? What kind of cosmic insights do they unlock?
Well, they provide two mind-blowing examples. First, they show how to solve the equation in the curved spacetime surrounding a black hole, which is described by something called the Schwarzschild metric.
Wait, they're using this math to understand what happens around the black hole. That's incredible. Can they really do that?
They can, and it's a testament to the power of mathematical generalization. By extending the Burger's equation to these extreme environments, we gain new insights into the nature of gravity and the fabric of spacetime.
Wow, that's seriously impressive. And what about their second example? What other cosmic wonders do they explore?
Their second example involves something called a cigar soliton.
A cigar soliton. That sounds like something you'd find in a Salvador Dali painting. What in the world is that?
It's a fascinating geometric object that represents a solution to a particular geometric flow equation. Imagine a shape that can evolve over time while maintaining its fundamental form.
Okay, so it's like a mathematical cigar that can stretch and bend, but always retains its cigar-like essence.
Yeah.
And they can apply this generalized Burger's equation to this strange object.
They can, and they provide a detailed explanation of how they derive the solution, including all the calculations involved. It's quite a technical tour de force.
This is definitely a deep dive for the mathematically adventurous. I need a moment to process all of this, but I'm ready for more. What other mathematical marvels await us in this research paper?
Let's explore another fascinating aspect of this research. They delve into solving Burger's type operator equations using the concept of invariant spaces, something we touched on earlier.
Right, invariant spaces.
Yeah.
It's about finding those mathematical objects that stay the same even when you apply certain transformations.
Precisely. The researchers utilize these invariant spaces to simplify the process of solving these complex equations. They demonstrate that if specific conditions are met, a function can be a solution to these generalized Burger's equations. These conditions involve carefully chosen differential operators and a vector space of functions with particular properties.
Okay, that sounds pretty abstract. Could you give us a concrete example to help us wrap our heads around it?
Absolutely. Let's imagine a scenario where we have differential operators, like partial derivatives with respect to x,
Okay.
and a linear operator, L, that acts on functions of x. The researchers show that if we can find a vector space of functions that satisfy certain conditions related to these operators, we can construct solutions to the Burger's type equation.
So it's like finding the right ingredients in the form of functions and operators, and then combining them in a specific way to cook up a solution.
That's a delicious analogy.
I'm starting to see how these invariant spaces can be a powerful tool for simplifying complex problems.
They really are. And what's even more fascinating is that they can combine this technique with fractional derivatives.
Fractional derivatives again, those seem to pop up everywhere in this paper.
They do. And for good reason. They provide a unique and powerful way to extend and generalize the traditional tools of calculus.
So they're not just introducing these concepts for the sake of complexity. They're showcasing how these seemingly abstract mathematical objects have real-world relevance and can be applied to solve complex problems.
You're absolutely right. They demonstrate this with compelling examples, including one that connects to the well-known concept of Brownian motion on a hyperbolic plane.
Hold on, Brownian motion. Isn't that the random jiggling of particles suspended in a fluid? What does that have to do with Burger's equations?
It's a fascinating connection. By choosing the right operators and functions, the researchers show that the solutions to a particular type of generalized Burger's equation can actually be related to the solutions of the differential equation that describes hyperbolic Brownian motion.
Wow, that's unexpected. It was like finding a hidden tunnel between two seemingly separate mathematical worlds.
Exactly. This connection highlights the deep interconnectedness of mathematical concepts, and it demonstrates the power of generalization. By extending and modifying familiar mathematical tools, we gain insights into a wider range of phenomena, even those that seem completely unrelated at first glance.
This is truly expanding my mathematical horizons.
Okay.
So we've seen how they solve these equations using invariant spaces and fractional derivatives. Do they explore any other techniques?
They do. They also explore the possibility of solving a simpler type of equation, a heat-type operator equation, by utilizing the solutions they obtained for the non-homogeneous Burger's type equations. It's like working backwards using the solution of a more complex problem to solve a simpler one.
That's a clever approach. So they're not just finding solutions, they're building connections and pathways between different mathematical concepts.
Precisely. They illustrate this approach with insightful examples. In one example, they start with a specific non-homogeneous Burger's type equation that we've discussed earlier. They've already demonstrated how to solve this equation using the method of invariant spaces and found a solution involving a function of time multiplied by a combination of the spatial variable x and a constant.
Right, I remember that solution.
Now, to solve the corresponding heat type equation, they use a special function often denoted as g.
G. That's the mathematical translator we talked about before.
Mm.
It takes the solution from one equation and maps it onto another.
Exactly. They show that by applying g to the solution of the Burgers type equation, you can obtain a solution to the heat type equation.
It's like using a decoder ring to translate between different mathematical languages.
That's a great analogy. They're revealing the intricate connections and relationships between different mathematical concepts.
This is incredible. They're not just solving equations, they're painting a bigger picture of how these mathematical ideas relate to each other.
Yeah.
It's like they're giving us a guided tour through the interconnected web of mathematical concepts.
Now, are you ready for the grand finale?
I think so. Hit me with it.
In the final section of the paper, they explore a multi-dimensional generalization of the non-homogeneous Burgers type operator equation.
Multi-dimensional. So we're going beyond just one spatial dimension. I feel like we're about to enter a whole new level of mathematical complexity.
Yeah, we're moving from a flat map to a 3D globe, from a single line to a multi-dimensional space.
Okay, my mathematical imagination is running wild. How do they handle this leap in complexity?
They introduce some incredibly sophisticated tools and concepts. One of the key players is the Laplace-Beltrami operator, which is a fundamental concept in differential geometry.
Differential geometry again. It seems like every step we take in this paper leads us deeper into the world of differential geometry. It's clearly essential for understanding these complex equations.
It is. They use the Laplace-Beltrami operator to model the equation on curved manifolds.
Curved manifolds. Are we talking about things like the curvature of space-time as described in Einstein's theory of relativity?
You're on the right track. And to showcase the power of this multidimensional generalization, they dive into two captivating examples. The first involves solving the equation in the curved spacetime surrounding a black hole described by the Schwarzschild metric.
Black holes again. I'm starting to think these researchers have a fascination with the most extreme objects in the universe.
It's certainly a fitting stage for exploring the limits of these mathematical equations. They guide us through the complex calculations, deriving a solution that describes the behavior of the generalized Burgers equation in this extreme gravitational environment.
It's mind-blowing to think that we can use math to probe the mysteries of black holes. What about their second example? What other cosmic wonders do they unveil?
Their second example focuses on a cigar soliton.
Wait, the cigar soliton? Didn't we encounter that earlier in the paper?
We did. It's that fascinating geometric object that arises in the study of geometric flow equations, a shape that can evolve over time while preserving its fundamental form.
Right, the mathematical cigar that never loses its shape.
Yeah.
It's incredible that they can apply this same generalized Burgers equation to such diverse phenomena.
It is. And they provide a detailed account of how they derived the solution, including the specific calculations involved. It's a testament to the power and versatility of these mathematical tools.
This entire deep dive has been a mathematical feast.
Yeah.
I'm so engrossed in this exploration. What other insights do they offer in this final section?
They delve into the nitty-gritty details of how they derived the solutions for both the black hole and cigar soliton examples.
Okay.
They walk us through the process of finding the invariant functions, calculating the coefficients,
Right.
and arriving at the final solutions, including the specific functions for each coordinate.
I'm starting to understand why they call this a deep dive. It's not just about understanding the what, but also the how. They're guiding us through every step of the mathematical reasoning and calculations.
Exactly. They're providing a comprehensive and insightful exploration of this fascinating topic.
I'm feeling a sense of awe and wonder at the beauty and power of mathematics. It's like we've been given a glimpse into the hidden architecture of the universe.
That's a beautiful way to put it. Mathematics is a language that allows us to perceive the underlying patterns and structures that govern reality. And this research paper is a testament to that profound truth.
Before we wrap up this section of our deep dive, let's take a moment to recap the key concepts we've covered so far. I want to make sure I've absorbed the essence of this mathematical adventure.
Absolutely. We began by introducing the concept of non-homogeneous generalizations of Burgers equations, essentially taking the classic Burgers equation and giving it a super-powered upgrade.
Right. It's like taking a basic tool and transforming it into a multi-purpose instrument capable of tackling all sorts of complex problems.
We then explored how these generalized equations can be solved using a variety of techniques, including transforming solutions from simpler equations,
Yes.
utilizing the concept of invariant spaces,
Right.
and even incorporating fractional derivatives.
It's amazing how they've woven together all these seemingly disparate mathematical concepts to unlock the secrets of these equations.
And to top it all off, we ventured into the realm of curved spacetimes, exploring solutions around a black hole and on a cigar soliton.
Those examples really stretched my imagination. They showed us how the power of mathematical generalization can be used to explore the most extreme and exotic phenomena in the universe.
It's been a thrilling exploration, hasn't it?
It certainly has.
Yeah.
Now, I'm eager to continue this journey and see what other mathematical marvels await us in the next section of our deep dive. All right, I'm ready to dive back in. What other fascinating concepts are hidden within this research paper?
Well, in one section, they explore a specific type of equation called a Burger's type operator equation and show how to solve it using the concept of invariant spaces. Remember those mathematical objects that stay the same even under transformations?
Right, like those steadfast friends who always stick together no matter what challenges come their way.
Yeah.
They're the ones you can always count on.
Exactly. Well, in the realm of mathematics, these invariant spaces can be incredibly useful for simplifying complex problems. The researchers demonstrate that if you can find the right invariant spaces, you can actually transform the Burger's type operator equation into a system of ordinary differential equations, which are generally easier to solve.
So it's like breaking down a complex puzzle into smaller, more manageable pieces.
I like it.
I like it.
And to make things even more interesting, they show that you can actually construct these invariant spaces. Using carefully chosen differential operators and a specific vector space of functions that satisfy certain conditions.
Okay, now it's starting to sound a bit abstract again.
Yeah.
Can you give us a concrete example to help us visualize this?
Sure. Let's consider a scenario where we have a differential operator, like the partial derivative with respect to x, and a linear operator denoted as L that acts on functions of x. The researchers demonstrate that if you can find a vector space of functions that meet specific conditions related to these operators, then you can use those functions to build an invariant space.
So it's like finding the right building blocks and then using them to create a stable structure that can withstand the forces of transformation.
That's a great way to think about it. And this technique opens up new avenues for solving these Burger's type operator equations.
It's incredible how they keep finding these clever connections between different mathematical concepts. It's like they're weaving together a tapestry of mathematical ideas.
Yeah.
What other surprises do they have in store for us?
Well, they don't stop there. Remember those fascinating fractional derivatives we discussed earlier?
Oh yes, those mind-bending extensions of the derivative concept. They're like taking the idea of a derivative and turning it up to 11.
That's a great way to put it. And in this section of the paper, they show how these fractional derivatives can be incorporated into these Burger's type operator equations.
So they're not just exploring these abstract mathematical objects for the sake of complexity. They're showing us how these concepts can be applied to solve real-world problems. I'm really starting to appreciate the depth and breadth of this research.
It's quite remarkable, isn't it? And they illustrate the power of these techniques with several compelling examples. One example even connects back to the concept of Brownian motion, which we touched upon earlier.
Wait, Brownian motion? Isn't that the random movement of particles suspended in a fluid? How on earth does that relate to these Burger's type operator equations?
It's a fascinating connection. Remember how we discussed the hyperbolic half-plane, that strange non-Euclidean space where parallel lines can meet?
Right.
Well, it turns out that by carefully choosing the operators and functions, the solutions to a particular type of generalized Burger's equation can be related to the solutions of the differential equation that describes Brownian motion on this hyperbolic half-plane.
Wow. It's like finding a secret passageway between two seemingly unrelated areas of mathematics.
It really highlights the interconnectedness of mathematical concepts and shows how powerful generalization can be. By extending and modifying familiar tools, we can gain insights into a wider range of phenomena, even those that seem completely unrelated at first glance.
This is truly expanding my mathematical horizons. I'm starting to see the world through a whole new set of mathematical lenses. So they've shown how to solve these Burger's type operator equations using invariant spaces and fractional derivatives. Do they explore any other approaches?
They do. They also investigate the possibility of solving a simpler type of equation, called a heat type operator equation. By utilizing the solutions they've already obtained for the non-homogeneous Burger's type equations, It's like working backwards, using the solution to a more complex problem to solve a simpler one.
That's a clever strategy. It's like using a master key to unlock a series of doors. Once you have the key, you can access a whole new set of possibilities.
Exactly. They demonstrate this approach with a couple of insightful examples. Let's walk through one of them to see how it works in practice.
Lead the way. I'm eager to see this reverse engineering process in action.
All right, let's start with a specific non-homogeneous Burgers type equation that we've discussed earlier. They've already shown how to solve this equation using the method of invariant spaces.
Okay, I recall that example. They found a solution that involves a function of time multiplied by a combination of the spatial variable x and a constant.
That's the one.
Yeah.
Now, to solve the corresponding heat type equation,
Okay.
they introduce a special function, often denoted as g.
Ah, G makes another appearance. It's like our trusty mathematical translator bridging the gap between different equations.
Exactly. And in this case, it acts as a transformer, taking the solution of the Burgers type equation and converting it into a solution for the heat type equation.
So they're essentially using G to decode the solution from the more complex equation and translate it into a solution for the simpler equation. It's like having a Rosetta Stone for mathematical languages.
That's a brilliant analogy. It highlights the beauty of this approach. They're not just solving equations in isolation.
Yeah.
They're revealing the underlying connections and relationships between different mathematical concepts.
This is truly a testament to the elegance and power of mathematical thinking. It's not just about crunching numbers, it's about understanding the deeper structure and relationships within the mathematical landscape.
Now prepare yourself, because in the next section, they take us on an adventure to a whole new level of generalization.
Okay.
They explore a multidimensional generalization of the non-homogeneous Burgers type operator equation.
Multidimensional. So we're going beyond just one spatial dimension. I feel like we're about to enter a whole new realm of mathematical complexity.
We are. It's like transitioning from a flat map to a 3D globe.
Okay, my mathematical imagination is in overdrive.
Yeah.
How do they even begin to tackle this increased level of complexity?
They bring in a whole arsenal of sophisticated mathematical tools and concepts. One of the key players is the Laplace-Beltrami operator, a fundamental concept in differential geometry.
Differential geometry again.
Yeah.
It seems like we can't escape its grasp in this paper. It's clearly essential for understanding these advanced concepts.
It truly is the language of curves, surfaces, and spaces. And the researchers use the Laplace-Beltrami operator to model the equation on curved manifolds.
Curved manifolds. Now we're talking about things like the curvature of space-time, like what Einstein described in his theory of relativity, right?
You're right on track. They show how this generalized Burgers equation in its multidimensional form can be applied to curved spacetimes, opening up the possibility of modeling all sorts of fascinating phenomena in cosmology and astrophysics.
Wow. So we're not just talking about abstract mathematical equations anymore. We're venturing into the realm of black holes, galaxies, and the very fabric of the universe itself. This is where math meets the grandest mysteries of the cosmos. What specific examples do they offer to illustrate this incredible connection?
Well, to show the power of this multidimensional generalization, they dive into two captivating examples.
Okay.
The first involves solving the equation in the curved spacetime surrounding a black hole described by the Schwarzschild metric.
Black holes. They really seem to be drawn to the most extreme and mind-boggling objects in the universe. What can these equations tell us about the behavior of space-time around a black hole?
They can tell us a lot. By applying this generalized Burgers equation to the Schwarzschild metric, which describes the gravitational field around a black hole, they're able to derive solutions that give us insights into how matter and energy behave in this extreme environment.
So they're using math to probe the deepest mysteries of black holes. That's absolutely incredible.
It's a testament to the power of mathematical modeling. And they don't just present the results, they guide us through the intricate calculations involved. They calculate the determinant of the metric tensor, the Laplace-Beltrami operator, and the individual contributions of the operator for each coordinate. It's a comprehensive analysis that reveals the beauty and complexity of this mathematical framework.
I can only imagine the level of mathematical sophistication involved in these calculations. But it's so inspiring to see how these abstract tools can be used to explore such profound physical phenomena. Now, what about their second example? What other cosmic wonders do they delve into?
For their second example, they return to a familiar friend, the cigar soliton.
Wait, the cigar soliton again? I thought we had already explored that fascinating geometric object.
We did, but remember we were working with a less generalized form of the equation earlier. Now armed with this multi-dimensional generalization, they revisit the cigar soliton to see what new insights they can uncover.
It's like revisiting a familiar landscape with a fresh perspective and a new set of tools. What new discoveries do they make on this second journey to the cigar soliton?
They show that even in this more complex multidimensional setting, the generalized Burger's equation can still be used to describe the behavior of this unique geometric object. They derive the solutions, including the specific functions for each coordinate, allowing us to visualize the evolution of the cigar soliton in this multidimensional space.
It's amazing how they've taken this mathematical tool and applied it to such a diverse range of phenomena, from shock waves in fluids to the curvature of space-time around black holes, and even to these abstract geometric objects like the cigar soliton.
It truly highlights the power and versatility of this mathematical framework. And they don't just present the solutions, they carefully explain the logic and calculations behind them, making this complex topic surprisingly accessible.
I'm starting to see why they call this a deep dive. It's not just about skimming the surface, it's about exploring the depths of these mathematical concepts and appreciating the intricate details of their application.
Now, are you ready for the final chapter of our mathematical adventure?
I'm ready. Lead the way. Okay, we've explored so many fascinating concepts in this deep dive. I'm ready to hear the researchers' final thoughts. What kind of big picture takeaways do they offer?
Well, they emphasize that their work isn't just about solving specific equations. It's about pushing the boundaries of mathematical understanding and showcasing the interconnectedness of seemingly disparate areas of mathematics.
That's been a recurring theme throughout this entire deep dive. We've seen how they've woven together concepts from calculus, differential equations, linear algebra, geometry, and even physics to create a rich and powerful mathematical framework.
Exactly. And they believe that this approach, the approach of generalizing and extending familiar mathematical tools, has the potential to unlock new insights and discoveries in a wide range of fields.
It's like they've given us a new set of mathematical lenses through which to view the world, revealing hidden connections and patterns that we might have missed before.
They also highlight the practical applications of their work.
That's important. It's easy to get lost in the abstract beauty of mathematics, but it's always grounding to see how these concepts can be applied to solve real-world problems.
They believe their generalized Burger's equation could be used to model complex phenomena in fields like fluid mechanics, cosmology, and even finance.
Wow, that's quite a range. So they're not just exploring these equations for the sake of pure mathematical curiosity. They envision their work having a real impact on our understanding of the world around us.
Precisely. They believe that their work opens up new avenues for research and could lead to advancements in various scientific and technological fields.
It's exciting to think about the possibilities. This deep dive has truly been an eye-opening experience. I feel like I've gained a newfound appreciation for the power and beauty of mathematics.
I am thrilled to hear that. And before we conclude, I have a final thought-provoking question for you to ponder.
I'm all ears. Bring on the final brain teaser.
We've seen the incredible potential of generalizing mathematical concepts. But what happens when we take this idea of generalization even further? What other equations, what other mathematical tools could we extend and reshape to uncover new truths about the world, truths we haven't even imagined yet?
Wow, that's a question that could keep me up all night. It's a reminder that the journey of mathematical discovery is never-ending. There are always new horizons to explore and new connections to uncover.
Exactly. And on that note, I think it's time to wrap up this deep dive.
Well, my brain is definitely full, but in a good way. Thanks for being such an incredible guide through this mathematical landscape.
It's been my pleasure. Remember, the exploration doesn't end here. Keep questioning, keep exploring, and keep diving deep into the world of mathematics.
And to all of you listening out there, thank you for joining us on this journey into the fascinating world of generalized Burger's equations. We hope you've enjoyed exploring the beauty, complexity, and incredible potential of mathematics. Until next time, stay curious. All right, so get ready, because we're going deep today, really deep, into the world of some pretty advanced math.
Oh, yeah.
Yeah, we're talking about a research paper, and this paper tackles something called the Burger's equation.
The Burger's equation, love it.
Now I know what you're thinking.
Yeah.
Math on a podcast. Are they serious?
Yeah. Who wants to listen to a math lecture?
But trust me on this. This stuff is fascinating, like seriously cool.
Oh, absolutely. This paper is all about how to make the Burger's equation even more powerful. You see, it's usually used for fluid mechanics, right? But these researchers, they figured out how to swap out some of the typical parts of the equation with these things called operators. They're more abstract mathematical tools.
Okay, so before we go any further, I think a little refresher is in order.
Definitely.
I mean, I vaguely remember the Burgers equation from back in the day, but
Yeah.
what is it actually? Like, what does it describe?
So imagine you've got a fluid, right? Like water or air. The Burgers equation, which, by the way, you can find it as equation 1.1 in the paper, it describes how the velocity of that fluid changes over time and also how it changes over space. So, like, it's used to model things like shock waves, you know, those sudden changes in pressure and density you see in explosions or like, around a supersonic jet.
Right. Okay. Yeah, those examples are definitely starting to jog my memory.
Yeah.
But you mentioned these researchers and how they're generalizing the Burgers equation. So help me understand that. What does that actually mean in practice?
It's kind of like you have a tool, right? A tool designed to do a specific job.
Okay, yeah.
But then you modify that tool so it can do a bunch more stuff. So in this case, what they do is they replace specific parts of the Burgers equation, the parts that are tied to fluid velocity, and they swap those out with these more general operators.
Operators, right. Vaguely rings a bell. I think I might have blocked out some of my math classes. Can you remind me what those are again?
Okay, so think about operators as like actions that you perform on functions. Sort of like verbs are actions in a sentence, right?
Okay, yeah, I get that.
So they take a function as input, and then they spit out a new function as output. For example, if you take the derivative of a function...
Oh, yeah, from calculus.
Exactly. That's
Yep.
actually an operator. It takes a function, and it tells you how it's changing at every single point.
Okay, yeah, I think it's starting to come back to me a bit. So let me see if I've got this right. They're essentially taking specific parts of this equation, and they're swapping them out with more general actions. Sort of like they're replacing specific verbs with more versatile verbs that can act on a wider range of functions. Is that right?
That is a perfect way to put it.
Okay, great. So what does that actually allow them to do? Like, what's the point of all this?
Well, the cool thing is, by doing this little swap, they can connect the solutions of their modified Burgers equation to the solutions of all sorts of other equations that you would never normally think are related.
Oh, wow, okay. So it's like they found some secret tunnel connecting different parts of the mathematical world. I like that analogy.
Yeah, it is. It's like a secret passage.
So give me an example. What kind of mathematical destinations are we talking about here? What other equations does this connect to?
So one of the most remarkable connections they make is to the heat equation.
The heat equation.
It describes how heat spreads, you know, over time, like how it diffuses. And you see this equation everywhere. Physics, engineering, even modeling financial markets.
So we're going from shock waves in fluids to like how heat spreads through a metal bar. That's a pretty big jump. I'm curious, how do they even start to connect those two worlds?
Well, the key is this special type of mathematical function called Hermite polynomials. Think of them like building blocks, right?
Right.
You can combine them in different ways to build up these really complex structures.
Okay, so Hermite polynomials, I think I've heard of them. But remind me, what's so special about them, especially in this research?
Well, they've got these really cool properties that allow the researchers to link the solutions of their modified Burgers equation to those solutions of the heat equation. It's like they found this common language, a language that both equations can speak.
So like a mathematical Rosetta Stone.
Exactly. A Rosetta Stone that lets you translate between the world of fluid dynamics and in the world of heat flow. Isn't that cool?
Yeah, that's amazing.
And that's really just the start. They actually take us on an even wilder journey. We go from there to exploring how their equation connects to this crazy thing called the hyperbolic plane.
Uh-oh, the hyperbolic plane. That sounds intimidating.
It is, but super fascinating. It's a non-Euclidean space. So it doesn't follow the normal rules of geometry that we learn in school. It's like, imagine a world where parallel lines actually meet, or where triangles can have angles that add up to way more than 180 degrees.
Okay, I'm trying to wrap my head around that. So they take this generalized Burgers equation and they apply it to this unique type of space. What happens? What's the big aha moment here?
This is where things get really cool. They found that one particular form of their generalized equation, it actually connects to how something called Brownian motion behaves on the hyperbolic plane.
Wait, Brownian motion. You mean like the random jittery motion of tiny particles suspended in a fluid?
That's exactly it.
Right.
So picture those tiny particles just bouncing around, constantly changing direction. And now imagine that dance happening on this warped, non-Euclidean surface.
Okay, my brain is doing backflips trying to picture that. But I'm still trying to connect the dots here. How does an equation designed to describe how a fluid flows connect to these randomly moving particles, especially on this, let's just say, unusual surface?
Right. It's all because of how they picked their operators. They were really clever about it. So by generalizing the Burger's equation in this specific way, they basically built a bridge between these two totally different worlds, the world of fluid mechanics and the world of random particle motion. And here's the kicker. A solution related to Brownian motion on the hyperbolic plane can actually lead to a solution for this particular type of Burger's equation.
So they're saying that by understanding those chaotic little particles, we can actually gain insights into how fluids behave. That's incredible.
Right. Pretty cool. And this is just the tip of the iceberg. The researchers go even deeper. They explore how concepts like invariant spaces and fractional derivatives can be used to solve their equation, and they even apply it to even more complex scenarios, like, get this, the curved spacetime of Einstein's general relativity.
Whoa, hold on. Curved space-time. We're talking black holes in the fabric of the universe now.
Oh, yeah.
All right, you've officially got my attention. Lead the way.
Okay, so curved spacetime, Einstein, general relativity, all that fun stuff.
Yeah, the universe bending and warping.
Exactly. But before we get to all the crazy stuff about curved spacetime, we have to talk about those terms you mentioned earlier. What were they again?
Oh, right. Invariant spaces and fractional derivatives. Those were definitely the ones that caught my attention.
Yeah, they're pretty wild concepts. Let's start with invariant spaces. They sound kind of mysterious, don't they?
Yeah, a little bit. What are they exactly?
Okay, so imagine you've got this whole bunch of functions, right? Like a toolbox full of different mathematical tools. An invariant space is a special set of those functions. Functions that, well, they stay the same even when you do certain operations to them.
So they're like, what, mathematical chameleons? They change their appearance, but their core identity stays the same.
Exactly. Like shapeshifters. They can transform, but deep down, they're still the same.
Okay, I like that. So how do these invariant spaces help us with this generalized Burger's equation?
Well, they can actually help us crack the code. Find solutions that might be really hard to find otherwise. It's like they give you a shortcut, a way to navigate through this complex mathematical maze.
So they're like a secret weapon for mathematicians.
That's a great way to put it. They're a secret weapon helping us unlock the secrets of these equations.
I love it. Okay, so what about fractional derivatives? Now, those sound like something straight out of science fiction.
I know, right? But they're actually a pretty natural extension of the derivatives you learn about in calculus. You've got your first derivative, your second derivative, and so on.
Yeah, those tell you how a function is changing, right, at a particular point or over a certain time period.
Exactly. But fractional derivatives, they let us explore derivatives of any order, even fractions like 1/2 or 3/4.
Okay, wait. So we're not just talking about the whole number derivatives. We're talking about fractions of derivatives. That's pretty wild. What does that even mean?
It's like taking the idea of change and breaking it down into even smaller, more nuanced pieces.
Okay, so like imagine you're tracking the speed of a car.
Right.
The usual derivatives, those would tell you the speed at a particular moment or the average speed over a certain time. But these fractional derivatives, they would give you this much more fine-grained picture of how that speed is changing between those moments.
Precisely. You're capturing these tiny fluctuations, these subtle changes that you might miss otherwise.
It's like zooming in on the concept of change itself.
Exactly. And you know what? These fractional derivatives they're actually super useful for modeling complex phenomena in the real world, things that don't quite fit into our normal categories of mathematical tools.
Okay, give me an example. Where do we see these fractional derivatives in action?
So in material science, for example, they can describe how materials with memory behave. Or in finance, where things are unpredictable, they can help model how stock prices fluctuate, all those crazy ups and downs.
So they're like a secret decoder ring for all the messy complexity of the real world.
You got it.
Right.
And what these researchers do in this paper is, well, it's pretty ingenious. They combine these two powerful concepts, invariant spaces, which are all about resisting change, and fractional derivatives, which are all about the nuances of change. They bring those two together.
Whoa, that's interesting. Two opposite ideas working together. So what happens when you combine these two concepts? What do they achieve by bringing them together?
They create a whole new way of solving this generalized Burger's equation, especially in situations where, get this, space-time itself is curved.
Okay, curved space-time. That's where things start to get really mind-bending. I've always loved the analogy that the universe is like a giant trampoline. you know?
Oh, yeah. A cosmic trampoline.
And then, like, massive objects, stars, planets, they warp that fabric, creating what we feel is gravity.
Exactly. That's such a great way to visualize it and to actually describe that warping mathematically, especially around really dense objects like black holes. We use something called the Schwarzschild metric.
Black holes. Okay, now we're talking. Regions of space-time where gravity is so strong, nothing can escape, not even light.
Pretty intense, right?
Yeah.
And so these researchers, they take their generalized Burger's equation with all its cool new features, the general operators, those invariant spaces, the fractional derivatives, the whole shebang, and they apply it to this curved space-time, this warped trampoline described by the Schwarzschild metric.
Hold on. So they're taking an equation that started out describing fluid flow, and now they're using it to explore what happens around a black hole.
Exactly. That's the beauty of generalization in mathematics. You abstract these ideas, you extend them, and suddenly you have this framework that can be applied to all sorts of crazy phenomena. It's like finding this universal key that can unlock the secrets of everything, from ripples in a pond to the warping of space-time itself.
Okay, that's mind-blowing. But I have to ask, how do they actually do that? How do you apply an equation designed for fluids to something as extreme as a black hole? What kind of mathematical magic are they using?
Well, they use another really fascinating equation called the Ritchie-Hamilton flow equation. And this equation, it describes how the shape of a geometric object evolves over time. So imagine you're watching a sculptor mold a piece of clay.
Right.
It's changing, it's morphing, it's flowing over time. That's what this equation captures.
Okay, I'm trying to picture that. So how does this flow equation connect to the generalized Burger's equation and all this stuff about curved spacetime?
The connection is through these special solutions to the Ritchie-Hamilton flow equation called Ricci-solitons. And Ricci-solitons, they're like geometric shapes that they keep their fundamental form even as they're changing, expanding or contracting. Imagine a balloon, right? You can inflate it, you can deflate it, but it's still a sphere.
No, it's like the essence of the shape remains constant.
Exactly. And so what the researchers do is they apply their generalized Burger's equation to scenarios involving these Ricci-solitons in curved space-time. And that allows them to explore how things behave, how fluids or other systems are influenced by the curvature of space-time itself.
Okay, my head is officially spinning. We've gone from shock waves and fluids to heat diffusion to the crazy world of the hyperbolic plane, and now we're exploring how shapes evolve in curved space-time. And it all started with this one generalized equation.
It's a pretty wild ride, isn't it? It really highlights something profound about, math and physics. It's like these ideas, these concepts that seem totally unrelated, they can be connected in these really surprising and beautiful ways. And it just shows you that there's this hidden tapestry of connections, this underlying structure to reality itself.
That's beautifully said. But I have to admit, with all this mind-bending math and physics, a part of me is still wondering, what does this all mean for me? Like the average person. How does this research actually connect to the real world, to the things I experience every day?
That's a great question, and it's one we should always ask when we're diving into these complex scientific topics. I mean, knowledge is at its best when we can understand it, appreciate it, and, apply it to our lives, apply it to how we see the world.
So what's the takeaway here? Like, what's the so what of all this research? What are the practical implications of all these connections they've uncovered?
Well, on a really basic level, this research is about pushing the boundaries of what we know and how we think. It's about finding new ways to analyze and understand these really complex systems, from things we're familiar with, like fluids and heat, to things that are, mind-boggling, like black holes in the universe itself.
I like that. But I have to be honest, some of those details are still a little fuzzy for me. Can you give me like a concrete example of what this research could actually be used for in the real world?
Sure. So remember we talked about the Schwarzschild metric, the one that describes how space-time is curved around a black hole?
Yeah.
So by applying their generalized Burger's equation to this, researchers could potentially unlock new insights into what happens when matter falls into a black hole. They could study how all that intense gravity warps and distorts how matter flows, and that could tell us so much more about the nature of black holes themselves.
So wait, they could use math to create a simulation of what happens at the very edge of a black hole, where gravity is so strong it warps both space and time.
Exactly. It's like having this mathematical microscope, it lets you zoom in on these extreme environments and study the fundamental laws of physics that are at play.
That's incredible. So it's not just abstract equations here. This research could lead to real discoveries about the universe. helping us answer some of the biggest questions about space, time, and gravity.
Exactly. And while the details might seem a bit intimidating, the key takeaway is this. Seemingly unrelated areas of science and math, they can be connected in these really surprising and profound ways. And this research really shows us the power of generalization in mathematics. It shows us that by taking these familiar concepts and abstracting them, extending them, we can create these tools that can be used to understand all sorts of phenomena. And ultimately, it leads to new discoveries and a deeper understanding of the world around us.
That's amazing. It's like finding these hidden patterns in a world that seems chaotic, revealing this beautiful order beneath the surface. It makes you wonder what other connections are still out there, just waiting to be discovered, what other secrets the universe is hiding.
And that's the beauty of science, isn't it? It's this never-ending journey of exploration, constantly pushing the boundaries of what we know, challenging our assumptions about the world. And this research, it's a perfect example of that. It shows us that even the most abstract mathematical ideas, they can have these profound implications for understanding the universe.
This has been incredible. Seriously, an amazing deep dive. We've covered so much from the basics of the Burger's equation to black holes and curved space-time. I feel like I've just had a crash course in advanced physics.
It has been quite a journey, hasn't it? And it's exciting to think about, what other connections, what other applications might come out of this research in the future. It really feels like the possibilities are endless.
On that note, I think it's time to wrap up this part of our deep dive. But before we go, I want to leave our listeners with something to think about. If math can connect something as random as, the motion of tiny particles to the swirling chaos at the edge of a black hole, what other hidden connections might be out there? What other secrets could we unlock through math? It's a pretty amazing thought.
Those are some great questions to ponder. And to all our listeners out there, I encourage you to, keep exploring, keep questioning, keep pushing those boundaries of knowledge. Because as we've seen today, the most incredible discoveries, they often happen at the intersection of these seemingly unrelated fields. It's about those curious minds, connecting the dots and revealing the hidden beauty and order of the universe.
Beautifully said. So keep those minds curious and those imaginations firing. We'll be back soon with the final part of this deep dive, so stay tuned. All right, so we've talked about black holes, curved space-time, all that crazy stuff. But I'm curious, are there any other examples, like specific examples, of what this research could actually unlock?
Oh, definitely. In fact, let's shift gears a bit away from those black holes and look at another cool thing they explored in the paper. They actually found connections between the generalized Burger's equation and something called the Schrödinger equation.
The Schrödinger equation. That sounds familiar. I think I remember that from my quantum mechanics class. It's all about how particles behave at the really tiny level, right? The atomic level and smaller.
You got it. It's basically the rule book for the quantum world. It describes how the wave function of a particle evolves over time. And get this, these researchers figured out a way to connect their generalized Burger's equation, the one we've been talking about, to this whole quantum realm.
Wait, hold on. So we're connecting fluid dynamics to, the behavior of electrons and stuff now. How is that even possible?
It's those operators again. Remember how they generalized the Burger's equation by replacing specific terms with those more general ones? Well, it turns out that if you choose the right types of operators, you can actually create a link between the solutions of the generalized Burger's equation and the solutions of the Schrödinger equation. It's like finding a secret passageway between the world of, swirling water and the world of tiny particles.
So you're saying that the same mathematical framework that describes how water goes down a drain could also describe how an electron orbits an atom.
Exactly. And that's why this research is so groundbreaking. It's not just about solving one particular equation or modeling one specific thing. It's about finding these unifying principles that connect these totally different areas of science. It's about showing how everything is connected and there are these patterns, these hidden patterns beneath the surface of all this complexity.
I love that. It really shows how powerful math is. I mean, it helps us understand the universe, from the tiniest particles to the biggest structures. But I got to ask, what's the point of connecting the Burger's equation to the Schrödinger equation? What could we actually do with that?
Well, one potential application is in the field of quantum computing. Quantum computers, they use those weird counterintuitive laws of quantum mechanics to perform calculations in ways that, normal computers just can't.
Yeah, I've heard about that. Quantum computers are supposed to be, like super powerful, right? But
Yeah.
also really hard to build.
Exactly. And one of the biggest challenges is controlling those quantum states. They're so fragile, so prone to errors. It's like trying to build a house of cards on a windy day.
Okay, yeah, I get the picture. So how does this research help with that?
Well, by connecting the generalized Burger's equation to the Schrödinger equation, researchers might be able to figure out new ways to, like, control and stabilize those delicate quantum states. Imagine if we could use the principles of fluid dynamics, something we're pretty good at understanding, to help us tame the wild world of quantum mechanics.
That would be incredible. It would
Uh,
completely change the game for quantum computing.
yeah.
Imagine all the problems we could solve if we could actually build these powerful quantum computers.
Right. The possibilities are mind-blowing, and that's just one example of how this research could have a huge impact on all sorts of different fields.
Wow. So we've gone from fluids to black holes to quantum mechanics, and it all started with just one equation.
It's been quite a journey,
Yep.
and it really just shows how important fundamental research is. Sometimes you have to explore these abstract concepts, even if you don't know exactly where they're going to lead. You never know what amazing discoveries might be waiting around the corner and how they might change our understanding of the world.
Absolutely. So as we wrap up this incredible deep dive, what's the one big thing you want our listeners to take away from all this?
I think the main takeaway is the power of generalization in math, in science, in life, really. It's about finding those underlying principles that connect things, those hidden patterns that show us the beauty and the order beneath the surface. It's about remembering that everything is connected and that by exploring those connections, we can unlock amazing new insights and possibilities.
Beautifully said. And on that note, I think it's time to wrap up this deep dive. It's been an incredible journey exploring all these fascinating connections and ideas. To all our listeners out there, keep those minds curious and never stop exploring those hidden connections. And until next time, happy deep diving. All right, everyone, get ready, because today we're going deep, really deep into some serious math. You guys requested we take a look at Burger's equations, but not the kind you throw on the grill, right? We're talking about a non-homogeneous generalization of them. And get this, we'll be uncovering links to some pretty unexpected areas, like hyperbolic Brownian motion, and even, get this, fractional
This
derivatives.
is going to be a fascinating journey.
Oh, it sounds like it. Our main course today is, and I'll try to say this right, this research paper titled A Non-Homogeneous Generalization of Burger's Equations. Ready to dive in?
Absolutely, let's do it.
Okay, so before we get too far, can you remind us what a standard Burger's equation actually represents?
Of course. The standard Burger's equation is, well, it's a model that describes how fluids behave. It captures how, the velocity of a fluid changes, like over time and space. It factors in things like viscosity and pressure.
So like water flowing through a pipe, or, I don't know, air moving over an airplane wing.
Exactly. It's really a fundamental equation in fluid dynamics. But the thing is, the standard Burger's equation has its limitations. It works well for, relatively simple scenarios. But when things get more complex, we need more powerful tools.
And that's where this research paper comes in.
Precisely. This paper wants to create a more general version of the Burger's equation that can handle more complex, more intricate phenomena. So instead of just simple fluids, this generalized equation could model things like the behavior of complex fluids, like polymers, or even, think about this, the dynamics of traffic flow, or even financial markets.
Wow, that's a pretty big leap. How do they even begin to generalize something as fundamental as the Burger's equation?
The key is in replacing the standard derivatives with more complex operators. So in the standard Burger's equation, the way the fluid, the velocity changes, that's described using derivatives. It tells us how a quantity changes, with respect to another quantity. But this paper introduces the idea of using more general operators that can capture, let's say, more nuanced and more complex relationships between those quantities.
Okay, I may need a little help here. Can you unpack this whole operator concept a bit? What exactly does that mean?
Think of an operator as, let's say, a mathematical machine. It takes an input, performs a specific action on it, and then spits out an output. So in the standard Burger's equation, that machine is just a simple derivative. But in this generalized version, we can use more elaborate machines, I guess, ones that can do, more sophisticated things to that input.
So it's like, I don't know, upgrading from a basic hammer to a whole multi-tool.
That's a great analogy. With a hammer, all you can really do is hit things. But with a multi-tool, you have a whole range of options. You can screw, you can saw, you can cut. Similarly, using more general operators, we can describe a much wider range of phenomena, much more than we could with just simple derivatives.
Makes sense. So instead of just describing how a quantity changes smoothly over time, these operators can capture, more complex behavior, like, I don't know, sudden jumps or oscillations.
Exactly. It's like going from, a simple straight line to a curve, one with all sorts of twists and turns.
Okay, so this paper swaps out those standard derivatives in the Burger's equation with these more general operators. And then what? What do they do with this new souped-up equation?
Well, the paper explores this generalization in a couple of key ways. First, they investigate how this new equation behaves in multiple spatial dimensions. See, the standard Burger's equation usually deals with just one spatial dimension, like, fluid flowing along a line. But in the real world, things happen in 3 dimensions.
Right, like water flowing through a pipe has to move in all directions.
Exactly. So this paper extends that generalized Burger's equation to encompass multiple spatial dimensions, which allows us to model more realistic scenarios.
That makes sense. So they've replaced the standard derivatives with these fancy operators, and they've expanded the equation to handle multiple dimensions. But now the million-dollar question, how do they actually solve this new, more complex equation? It all sounds pretty abstract.
That's a great question. And that's really where the heart of this research lies. The paper outlines 2 main methods for finding solutions to these generalized Burger's equations.
2 methods. Okay, I'm all ears. Tell me about method number 1.
The first method involves transforming solutions of simpler linear equations into solutions for these more complex generalized Burger's equations.
Wait, so you're saying they can take solutions from a different type of equation and somehow morph them into solutions for this new generalized Burger's equation?
Exactly. It's like finding a secret passageway between 2 seemingly different worlds. But there's a catch. It only works under certain conditions. The operators involved have to, let's say, play nicely with each other for this transformation to work.
Uh-oh, I'm sensing some mathematical jargon coming on.
Yeah.
Can you break down what you mean by playing nicely?
Essentially, it means that the order in which you apply these operators shouldn't matter. If you switch the order, you should still get the same result. Mathematically, we call this the commutativity property.
So it's like if you're getting dressed in the morning, it doesn't matter if you put on your socks first and then your shoes, or your shoes first and then your socks. You'll end up dressed either way.
That's a great analogy. But if you tried to put on your pants after your shoes, well, that wouldn't work out so well. In the same way, if the operators don't commute, this transformation method falls apart.
Okay, I think I'm following. So to use this first method, we need operators that commute, meaning the order we apply them in doesn't affect the outcome. Is there anything else we need to keep in mind?
Another crucial property is the Leibniz property. This property essentially describes how an operator behaves when applied to a product of 2 functions.
A product of 2 functions. Can you give me an example?
Sure. Imagine for 2 functions. Let's say fx equals x squared and gx equals sine of x. The product of these 2 functions would be fx times gx, which is x squared times sine of x. The Leibniz property, that tells us how an operator acts on this product.
So it's like having a special rule for how to apply the operator when you have, I guess, 2 functions multiplied together.
Exactly. And for this transformation method to work, the operators need to satisfy this Leibniz property. It makes sure the transformation process behaves, consistently and preserves the structure of the equations.
Got it. So we need operators that commute, and they got to satisfy the Leibniz property. Anything else?
One more thing, generalized Hermite polynomials.
Oh boy, those sound intimidating. Can you give me a crash course on what those are and why they matter?
They might sound scary, but they're actually pretty closely related to the standard Hermite polynomials, the ones you probably saw in calculus. Remember those?
Vaguely. They had something to do with derivatives and integrals, right?
Right. Hermite polynomials are a set of special functions that pop up all over math and physics. They have a specific form, and they have some interesting properties that make them useful for solving certain types of equations.
Okay, so they're like, I don't know, mathematical superheroes with special powers.
You could say that. Now, generalized Hermite polynomials are Well, a more general version of those superheroes. They're extended to fit this more complex framework we're working with, where we have these more general operators instead of just simple derivatives.
So it's like giving our mathematical superheroes a power-up so they can handle these more challenging tasks.
Exactly. And these generalized Hermite polynomials, they play a key role in this transformation method because, they help us map solutions from simpler equations to solutions of that generalized Burger's equation.
Okay, I'm starting to see the bigger picture here. To make this transformation magic happen, we need operators that behave well together, meaning they commute. They've got to satisfy the Leibniz property. And these Hermite polynomials come in handy along the way. Am I getting that right?
You got it. Now, to really see this in action, let's look at some specific examples. The paper takes us to the hyperbolic Poincaré half-plane. It's a type of geometric space with some unique properties.
Sounds exotic. I'm picturing something like, I don't know, the surface of a donut.
It's not quite like a donut, but it's definitely a fascinating space. And the authors use this space to demonstrate how that transformation method works.
Okay, I'm ready to see some math in action. Walk me through it.
In the first example, they use a specific coordinate system on this hyperbolic half-plane, a way to pinpoint locations. It's called the coordinate of the arc length of geodesics, denoted by the Greek letter eta, but you can think of it as, a way to measure distance in this curved space.
So instead of using our familiar x and y coordinates, they're using this eta coordinate to navigate this weird hyperbolic world.
Exactly. And they define two operators, n and o. The operator n that acts on functions of eta, meaning it does something to functions that depend on this distance coordinate, and the operator o that acts on functions of time denoted by t.
So n is all about how things change over distance in this hyperbolic space, and o is all about how things change over time.
Precisely. With these operators in place, that generalized Burger's equation takes on a specific form.
So we're seeing how the general equation can be tailored to this particular hyperbolic setting.
You got it. And now comes the cool part, the transformation. They show that if you choose a function, let's call it g, you can transform solutions of a simpler linear equation into solutions of this more complex Burger's equation.
Okay, so this function g is like, I don't know, a magic key that unlocks the solution.
You could say that. And in this particular example, the solution they find using this transformation, it involves a generalized Hermite polynomial, just like we talked about.
It's all coming together. So they start with a simpler equation. Apply this transformation using the function g, and out pops a solution to the generalized Burger's equation in this hyperbolic space, complete with a Hermite polynomial.
You've got it. And the second example follows a very similar pattern. They use a slightly different set of operators, but it's on the same hyperbolic Poincaré half-plane. But the overall strategy is the same. Transform solutions of a simpler equation into solutions of the generalized Burger's equation.
And they find another solution involving a generalized Hermite polynomial.
Yep. It's a different polynomial, of course, because the operators and coordinate systems are different, but the underlying principle is the same. They're essentially showing that this transformation method, it's a versatile tool. It can be adapted to different situations.
Okay, this is starting to make sense.
Yeah.
Now, you mentioned earlier something about a connection to Brownian motion. That seems to come completely out of left field. How does, I don't know, random movement like that relate to fluid flow?
It's one of the most fascinating aspects of this paper. The third example, it actually links the generalized Burger's equation to, believe it or not, hyperbolic Brownian motion.
Hold on, I thought Brownian motion was about, like, dust particles jiggling around randomly in the air.
It is. Imagine a particle randomly bouncing around on this hyperbolic surface. The solution to the generalized Burger's equation, in this case, it tells you something about the behavior of that particle over time.
So the solution isn't describing the flow of a fluid, but the movement of a randomly jiggling particle.
That's a good way to think about it. But there's a technical detail here. The initial condition for this Brownian motion involves something called a Dirac delta function, which can lead to some, tricky math because of the natural logarithm that appears in the solution.
Dirac delta function, that rings a bell. It's that function that's zero everywhere except at one point, right?
Exactly. It's a mathematical tool used to represent, like a point-like source or a sudden impulse. And because of that, you have to be careful when choosing the time point you're looking at to avoid mathematical problems.
You can't just plug in any time you want.
Right. You have to pick a time that works well with this initial condition. It's a subtle point, but it highlights the importance of, paying attention to the details when working with these equations.
Okay, I'm trying to keep all this straight. So We've covered this first method of solving the generalized Burger's equation, which involves transforming solutions from simpler equations. Are you ready to tackle the second method?
Absolutely. Let's dive into the invariant spaces method.
All right, my brain is buzzing after that first method. It's amazing how they can, pull solutions from other equations to solve this generalized Burger's equation. But you mentioned there's a second method, the invariant spaces method. What's that all about?
This method is all about, well, finding those special spaces of functions, spaces that remain, let's say, unchanged when you act on them by those operators involved in our equation. We call these spaces invariant spaces.
Okay, that sounds pretty abstract. Can you, paint a picture for me? What does it mean for a space of functions to be, invariant?
Imagine a potter shaping clay on a spinning wheel. As the wheel spins, the clay's position changes, right? But its shape, molded by the potter's hands, stays the same.
So the shape of the clay is invariant under that spinning motion.
Exactly. Now, instead of clay, picture a collection of functions. And instead of spinning, imagine applying those differential operators, the ones we've been talking about.
So we're looking for groups of functions that, stay the same, even after being transformed by these operators.
You got it. It's like these functions have a special immunity to the effects of those operators. And if we can find such a space, it becomes, let's say, much easier to construct solutions to that generalized Burger's equation.
That's pretty clever. Where do we even begin to find these magical invariant spaces?
The paper's appendix gives us a great starting point. It provides a step-by-step guide, I guess you could say, for finding these spaces. And it shows how to use them to solve specific examples of that generalized Burger's equation.
Sounds like a treasure map. So what kind of examples do they, tackle using this method?
They start with equations that involve fractional derivatives. It's a concept that kind of, expands our usual notion of derivatives.
Fractional derivatives. That sounds like something out of, I don't know, a science fiction novel.
It might sound strange, but it's a really powerful tool. Instead of just taking, the first, second, or third derivative, you can take a derivative of, let's say, order 1/2.
So it's like taking a derivative, but with a fraction as the order. How does that even work?
It's a bit more complicated than our usual derivatives, but the basic idea is similar. Think of it as, zooming in between those integer steps of differentiation.
Okay, my brain is trying to wrap itself around that one. So how do these fractional derivatives, how do they fit into the Burger's equation?
They replace some of those standard derivative terms in the equation, making it even more general, more capable of, capturing a wider range of phenomena.
In the invariant spaces method, that helps us solve these fractional Burger's equations.
Exactly. The authors use this method to solve several examples involving those fractional derivatives. And in the process, they introduce this special function called the Mittig-Leffler function. It's a mathematical tool specifically designed for dealing with fractional calculus.
So it's like adding a new specialized tool to our mathematical toolkit.
Precisely. And here's where things get really interesting. They found that you can sometimes get the same solution using different sets of operators.
Wait, so there are multiple ways to arrive at the same answer. It's like there are multiple paths, I guess, leading to the same destination in this mathematical jungle.
That's a great way to put it. It speaks to the interconnectedness of these concepts and the flexibility we have in approaching these equations.
This is blowing my mind. But wait, you mentioned that the invariant spaces method can solve more than just the generalized Burger's equation.
That's right. The solutions we find for that generalized Burger's equation, they can act as building blocks to solve other types of equations, specifically, linear equations, like the heat equation.
Wait, we're going from solving a, complex nonlinear equation to solving a simpler linear one? That seems, I don't know, counterintuitive.
It might seem strange, but that's the beauty of mathematics. The solutions we find for one type of equation can often be used to unlock the secrets of other, seemingly unrelated equations. It highlights those deep connections, the ones that underlie these mathematical concepts.
That's amazing. It's like solving one puzzle gives you the key to solving another.
Exactly. And the paper demonstrates this idea with, concrete examples. Again, using that hyperbolic Poincaré half-plane to make the concepts more tangible.
Okay, so we've seen how the invariant spaces method helps us solve that generalized Burger's equation in various forms, even those involving those fractional derivatives. Are we ready to level up again and tackle the challenge of generalizing to multiple dimensions?
Absolutely. This is where things get really exciting, especially when we start talking about, curved spaces and even the fabric of space-time itself.
Hold on, curved spaces? I thought we were dealing with, like, flat planes.
We were, but now we're taking it up a notch. The paper shows how to generalize that non-homogeneous Burger's equation to involve multiple spatial dimensions, which allows us to move beyond those, flat planes and into more complex curved spaces.
Okay, so instead of just moving along a line or on a flat surface,
Right.
we can now describe, phenomena happening on more intricate curved surfaces, like, I don't know, spheres or even something, I don't know, more exotic.
Precisely. And this generalization, it allows us to bring in those powerful concepts from geometry and physics, like the Laplace-Beltrami operator.
Laplace-Beltrami. That sounds like another one of those fancy math terms that make my head spin.
It might sound intimidating, but it's a really fundamental concept that pops up all over physics and geometry. It's a way to, measure how a function changes on a curved space. Think of it as a generalized version of the Laplacian operator, the one you probably saw in calculus. But now it works on curved surfaces instead of just those flat planes.
So it's like we're upgrading our mathematical toolbox, to handle the complexities of those curved spaces. But how does this Laplace-Beltrami operator, how does it fit into that generalized Burger's equation?
By incorporating this operator into the equation, we open up the possibility of studying these equations on, let's say, curved spaces, including those described by, Einstein's general theory of relativity.
Wait, relativity, as in black holes and, like, warping space-time. Now we're really going down the rabbit hole.
We are. And the paper doesn't just stop at the theoretical generalization. They actually provide a concrete example on the Schwarzschild spacetime, which describes the spacetime around a massive object, like a black hole.
Okay, I'm on the edge of my seat. Walk me through this. How do they apply this generalized Burger's equation to something as, mind-boggling as a black hole?
They start by, they meticulously calculate those key quantities, the ones needed to apply the equation in this context. One of these is the determinant of the metric tensor, a mathematical object that, essentially tells you how distances are measured in this curved space-time.
Metric tensor, another fancy term, but I'm starting to get the gist of it. It's all about how we measure distances in, like, different spaces, right?
Yeah.
Like how distances on a curved surface are different from distances on a flat plane.
Exactly. They also carefully calculate, those individual contributions to the Laplace-Beltrami operator, which, remember, tells us how our function changes in that curved space.
So they're breaking down that Laplace-Beltrami operator into, smaller, more manageable pieces to make it easier to work with in this specific spacetime.
Precisely. And once they have all these pieces in place, they use the invariant spaces method to find a solution to that generalized Burger's equation, in this curved space-time setting.
Incredible. So they're actually showing that these methods work, even in the most, I guess, extreme environments imaginable. It's like they're proving that these mathematical concepts, aren't just abstract ideas. They have real-world applications, even in the most, I don't know, mind-bending corners of the universe.
Yeah, absolutely. But as always, there are some technical details to keep in mind. They point out that the solution involves logarithmic functions, which can be a bit tricky to work with on curved spaces.
Those pesky logarithms again.
Yeah.
So we have to be careful about, like, the domain of our solution, just like we did with the Brownian motion example.
Exactly. We can't just plug in any values. We got to make sure they make sense within the context of this curved spacetime. It's a reminder that while these mathematical tools are powerful, we still need to use them, carefully and thoughtfully.
It's like a constant reminder that math isn't just about, like, blindly following formulas. It's about understanding the nuances and limitations of those formulas. Okay, we've tackled the Schwarzschild spacetime. What else is on the menu for this multidimensional feast?
For the grand finale, they take us to the cigar soliton.
Cigar soliton. That sounds intriguing. What exactly is that?
It's a solution to the Ricci flow equation, which describes how the geometry of a space changes over time. Imagine watching a movie of a space evolving, stretching, morphing over time.
Okay, so we're not talking about a static, unchanging space anymore, but a dynamic one that's constantly, evolving.
That's right. And the cigar soliton, it's special because it represents a space whose size changes, but its shape, that stays the same. It's like a balloon that, I don't know, inflates or deflates, but always, maintains that balloon-like shape.
I could almost picture it. So how does that generalized Burger's equation fit into this evolving space?
They show how to calculate a solution to the equation on this ever-changing cigar soliton space, demonstrating that those methods can handle even spaces that are, let's say, morphing and evolving over time.
So we've gone from simple fluids to black holes and now to spaces that are like changing and evolving right before our eyes. It's like
Yeah.
we've unlocked a whole new level of understanding
It is pretty amazing, isn't it? It's a testament to the power
and flexibility,
of the invariant spaces method.
making the generalized Burger's equation.
We've come such a long way from that basic fluid flow equation. We have. We've gone from simple derivatives to those fractional derivatives, from flat planes to curved spacetimes, and even to spaces that are, constantly changing over time. And we've seen how the invariant spaces method can be used to tackle these, increasingly complex challenges.
It's like we've, I don't know, scaled a mathematical mountain and now we're standing at the summit, taking in this breathtaking view of interconnected ideas.
That's a fantastic analogy. It's truly remarkable how these, seemingly abstract mathematical concepts can have such profound implications for understanding the world around us, from the smallest particles to the grandest cosmic structures.
All right, before we get, lost in the scenery up here, let's take a moment to catch our breath and recap this, this incredible journey so far. We started with that familiar Burger's equation, which describes that simple fluid flow. And then we embarked on a quest to generalize it, replacing those standard derivatives with more powerful, more versatile operators.
And along the way, we discovered that this seemingly simple equation could be used to describe a, much wider range of phenomena, from that random jiggling of particles in Brownian motion to the evolution of those curved spacetimes, even those around black holes.
We learned about two incredible methods for solving these generalized equations. The transformation method, which ingeniously uses solutions from simpler equations to unlock solutions for that generalized Burger's equation. And the invariant spaces method, which searches for those special groups of functions that, that remain unchanged, even after being acted upon by those complex operators.
And we saw how those methods can be applied to solve, specific examples, from equations involving those fascinating fractional derivatives to equations defined on curved spaces, like that Schwarzschild spacetime and the ever-changing cigar soliton.
It's been an incredible journey so far, but I have a feeling there's still so much more to uncover. Are you ready for the final leg of our adventure?
Absolutely. We've explored the theoretical foundations and tackled some mind-bending examples. Now let's delve into the implications of these findings, explore some of the unanswered questions, and uncover that vast potential that lies ahead.
It's been, wow, what a journey it's been so far. We've gone from simple fluids to black holes, from those flat planes to those evolving spaces. It's amazing to see how this one equation, that generalized Burger's equation, can be used to describe such a wide range of phenomena.
It is remarkable, isn't it? And we've only just begun to explore its potential.
That's what's so exciting. We've laid the groundwork, but there's still, so much more to uncover. Where do we go from here? What are the next steps in this mathematical adventure?
Well, one avenue we haven't really explored yet is the role of, numerical methods in solving these generalized equations. Remember, the paper, it focused primarily on finding those, elegant, exact solutions. But in the real world, those aren't always easy to come by.
Right. Sometimes those exact solutions are just, too complex or even impossible to find. So we need other tools in our arsenal to tackle these equations.
Exactly. And that's where, numerical methods come in. These methods provide a way to, approximate solutions using computers, allowing us to explore scenarios where exact solutions might be, a bit elusive.
So it's like we're using the power of computers to simulate the behavior of these, complex systems, even if we can't solve the equations, perfectly.
That's a great way to put it. And there's a whole world of numerical methods out there, each with its own, strengths and weaknesses. Some are better suited for, certain types of equations or specific, physical scenarios. Developing, robust and efficient numerical methods for those generalized Burger's equations, well, it's a crucial area for future research.
It's like we need a whole new set of, I guess, computational tools to unlock the secrets of these equations when those exact solutions aren't available. It's like we're, I don't know, building a bridge. Between that, the theoretical world of mathematics and the practical world of, of computation.
Precisely. And as we build that bridge, we'll be able to tackle even more, challenging problems, model even more, complex phenomena, and gain, deeper insights into the behavior of these systems.
So numerical methods are one path forward. What other, I don't know, directions for future research are you excited about?
Another exciting avenue is the development of even more, general mathematical frameworks. Remember those assumptions we had to make about, those operators and spaces involved. What happens if I don't know, if we relax those assumptions? Can we push the boundaries of the theory even further?
So it's like we're not content with just exploring this, this mathematical jungle. We want to, expand the jungle itself, discover new mathematical territories, and chart new courses through this uncharted wilderness.
Exactly. And as we push those boundaries, we might uncover new connections between seemingly unrelated fields of mathematics, leading to an even, I guess, richer and deeper understanding of those fundamental principles that, govern these equations.
It's like we're constantly redrawing the map of mathematics, revealing new landscapes, and forging new paths.
That's a fantastic way to think about it. And as we venture further into this uncharted territory, we're bound to encounter new challenges and obstacles, but that's what makes research so thrilling. It's the excitement of the unknown, the possibility of stumbling upon something truly groundbreaking.
It's like we're, pioneers, venturing into a new frontier, driven by, I don't know, curiosity and the thirst for knowledge.
Exactly. And who knows what treasures we might find along the way, new, mathematical concepts, unexpected connections, and perhaps even a deeper understanding of, of the universe itself.
Throughout this whole deep dive, we've been focusing on how these equations, how they can, help us understand the physical world, from fluid flow to the evolution of the cosmos. But now I'm wondering, could it be the other way around? Could these equations be telling us something, something deeper about the nature of, I don't know, reality itself?
That's a profound question, and one that's, puzzled philosophers and scientists for centuries. What if the universe, at its core is fundamentally mathematical? What if these equations, they're not just, tools for describing reality, but are like, glimpses into the very fabric of, of existence?
Well, that's a mind-blowing thought. It's like we're not just using math to understand the universe, but we're we're starting to wonder if math is the universe.
It's a tantalizing idea, isn't it? And while we may never, have a definitive answer, it's the pursuit of that answer that, that drives us to explore, to question, to push the boundaries of what we know.
I have a feeling that this deep dive, this is just the beginning of, of a much larger journey. It's sparked countless new questions, and I'm sure will inspire a whole new, generation
of mathematical explorers to venture into this fascinating realm.
It has been a truly remarkable journey. And remember, the adventure of, discovery that never truly ends. There's always, more to learn, more to explore, and more to wonder about.
Thank you so much for, for guiding us through this incredible, I guess, mathematical landscape. It's been an absolute privilege.
The pleasure was all mine. And to all of you listening out there, keep exploring, keep questioning, and never stop, wondering about the mysteries of the universe.
Yeah.
And the mathematical language that might just, unlock them.
And on that note, we'll wrap up this deep dive into the world of, generalized Burger's equations. We encourage you to, check out those links, ones provided in the show notes, and continue your own, I guess, exploration of this fascinating field. Until next time, keep those minds curious.
All right, let's dive into some really fascinating math today. We're taking on the Burger's equation. You might have heard of it, probably from fluid dynamics. But the paper we're looking at today, well, it kind of takes things to a whole new level. We're going to be thinking about things like swirling galaxies, or the crazy middle of a hurricane, even like how space-time bends around a black hole.
It's pretty amazing, this paper. It's called a non-homogeneous generalization of Burger's equations. And what gets me is how it sets up this math framework. And you can use it for so many different things. I mean, we're talking understanding complicated systems that, change over time, from tiny stuff to the really big.
So before we get like totally lost in all these equations, maybe we should start with something a little more down to earth, like, I don't know, traffic. Imagine you're stuck, right,
Yep.
in a traffic jam. And the speed of all the cars around you, it's changing all the time, right? And it depends on where you are on the highway. That's kind of what the Burger's equation is getting at, isn't it?
Yeah, you got it. The basic Burger's equation is where we're starting. And it's a partial differential equation. It describes how the velocity of something changes. Could be a fluid or even those cars in the traffic jam, right? Over time and space. And it really helps us understand like shock waves and turbulence, those sudden changes in speed and direction that make things, well, interesting.
Okay, so I'm looking at equation 1.1 in the paper here. It's the basic Burger's equation. I'm not even going to try to read that out loud. But maybe you could break it down for us a little. What are the main things that affect how velocity changes?
Sure. Think of it as a balance of different forces, right? You've got the internal friction in the fluid, and it's trying to make everything smooth. Then there's how the fluid naturally wants to spread out, like if you drop ink into water. And then, of course, you have any outside forces that are acting on it, like gravity or pressure. The Burger's equation shows how all those forces come together to make the fluid act the way it does.
Okay, so this paper, it takes that basic Burger's equation, right? And then it adds this new thing, this operator concept. I remember operators from way back in math class, but it's all kind of fuzzy now. Maybe a quick refresher.
Sure. Think of operators like mathematical machines. They change functions. So in the regular Burger's equation, you have specific derivatives. And those tell you how a function changes with, a certain variable, like time or space. But this paper, what it does, it replaces those specific derivatives with more general operators, gives you more flexibility, opens up a ton of new possibilities.
So it's like you're taking a simple tool and turning it into like a Swiss Army knife.
Yeah.
With all sorts of attachments. So you could do way more.
Yeah, that's a good way to think about it. These generalized Burger's equations, using these operators instead of those specific derivatives, it means we can describe a lot more different phenomena. It's not just regular fluid dynamics anymore.
All right, so let's talk solutions for a sec. How do you actually solve these generalized Burger's equations? I mean, for all the complexity we've been talking about, it sounds like really hard.
You're right. They are complex. But, mathematicians are pretty clever. The paper, it looks at two really ingenious ways to find solutions. The first one's called transformation. It's kind of like you have this really complicated puzzle, right? And you take all the pieces and rearrange them into a different puzzle, one you already know how to solve.
So you're turning the problem into something more familiar, easier to work with.
Right. They take this generalized Burger's equation and they do some mathematical manipulation and they turn it into something that looks like the heat equation, the one that describes how heat flows. And we know how to solve that one.
Wow, that's pretty neat. What about the second method? What's that one all about?
So the second method, it focuses on these things called invariant spaces. Basically, it's about finding like hidden patterns inside the equations, like symmetries. Or structures. And these let you simplify things, make it easier to pull out the solutions, like finding, I don't know, a secret code inside some complicated message. And the code unlocks the meaning.
Okay, so this is where things start getting really wild.
Yeah.
Now we're getting into Hermite polynomials. I kind of remember those from calculus. Something about like a special set of functions, maybe a quick reminder.
Right, Hermite polynomials. It's a whole family of polynomials. They have a specific form, and they have some really useful properties. You see them in all sorts of areas, actually. Math, physics,
Right.
From probability to quantum mechanics. And in this paper, they play a big part in finding solutions to the generalized Burger's equation, specifically in a very particular type of space. It's called the hyperbolic half-plane.
Whoa, hold on. Hyperbolic half-plane, that sounds like something straight out of Star Trek.
It might sound like sci-fi, but it's a real mathematical concept, and it's pretty fascinating. See, the hyperbolic half-plane, it's a non-Euclidean space. That means it doesn't follow the normal rules of geometry. The stuff we learned in school.
You mean all those theorems about parallel lines and triangles and stuff? They don't work here.
Not exactly. Imagine a world where like parallel lines can meet, and the angles of a triangle, they don't add up to 180 degrees. It's a mind-bending kind of world.
Okay, I'm trying to picture this. Why would we even want to solve the Burger's equation in this weird hyperbolic world? What's the point?
Good question. So the thing about the hyperbolic half-plane, even though it sounds super strange, it can actually be used to model real things, like in cosmology, to understand the structure of the universe on the really big scale. And in this paper, it's a unique environment for exploring solutions to this generalized Burger's equation.
So they're basically taking these generalized Burger's equations and applying them to this whole new kind of geometry, which could lead to some really new ways of understanding the universe.
Yeah, exactly. And examples 1 and 2 in the paper, they show how the generalized Burger's equation can describe fluid-like behaviors, not in the world we're used to, but in this warped, curved, hyperbolic half-plane.
All right, so I think I'm ready for the next mind-blowing idea. Let's talk about Brownian motion. That's the random movement of tiny particles in a fluid, right? How does that fit into all of this?
You got it. Brownian motion is all about randomness, unpredictable movement. And what's amazing is that example 3 in the paper, it shows how the solutions to the generalized Burger's equation, they can actually be connected to Brownian motion, specifically in the hyperbolic half-plane again.
Wait, so you're saying that this random dance of these tiny particles, it can be linked to this equation that describes how fluids flow in this warped geometry?
Yeah, exactly. It's like saying that the patterns of a hurricane, those swirls, could somehow be connected to, I don't know, how dust particles move randomly in the wind.
That's wild. How do they even start to make that connection?
The key is equation 2.24. It connects the generalized Burger's equation to something called the hyperbolic Laplacian. Laplacian is a mathematical operator, basically. It measures how things spread out or diffuse in a space. And in this case, it's the hyperbolic Laplacian. So it's measuring that spreading out, but in this warped geometry we were talking about.
So it's like saying how a fluid flows in this strange hyperbolic world is somehow related to how things spread out in that same space. That's pretty crazy.
And it's not just theoretical either. This connection to Brownian motion means these generalized Burger's equations could be useful in fields that need to understand random processes, like finance, or maybe even biology.
Okay, my mind is officially blown.
Yeah.
This is all way beyond what I imagined when we started talking about the Burger's equation. Where do we even go from here?
Well, believe it or not, the paper doesn't stop there. It takes things up a notch. By generalizing the equations even more, think about going from a one-lane road to a multi-lane highway. That's what they're doing here, moving from one spatial dimension to multiple dimensions.
So instead of just looking at how a fluid flows in a line, we're now talking about how it behaves in a plane, or even in three-dimensional space.
Exactly. Equation 4.1, that's where this multidimensional stuff happens. It brings in more complicated scenarios, like how heat flows in a solid object, or how particles move in a magnetic field.
That sounds incredibly complicated.
It is. But the paper, it has some amazing examples to show how these multidimensional generalizations actually work. Example 8, for instance, it uses the hyperbolic Laplacian, the whole thing, to solve a more intricate version of the generalized Burger's equation.
Okay, I think I need a break. We've covered so much. From basic Burger's equation stuff to Brownian motion and the hyperbolic half-plane. I can't wait to see what other surprises this paper has for us. All right, welcome back. Man, I'm still thinking about everything we talked about in the first part. I mean, it's amazing how one equation, this Burger's equation, can be generalized and applied to all these crazy scenarios.
Yeah, it really is remarkable. And we're really just getting started this paper. It goes even deeper. It looks at these specific techniques and examples, and they really show off how powerful these generalized Burger's equations can be.
One thing that really stood out to me was how the paper kind of goes back and forth between these abstract math ideas and these, concrete examples. It's like they're showing us the blueprints for these powerful math machines, and then, bam, they take us for a test drive to see how they work.
Absolutely. And one of the best examples of that is example 1. It focuses on finding solutions to the generalized Burger's equation in the hyperbolic half-plane using Hermite polynomials.
Right, and just to remind everyone, the hyperbolic half-plane is that non-Euclidean space we talked about, where parallel lines can meet and triangles have angles that add up to more than 180 degrees. It's a pretty wild concept, but the paper uses it to explore some really interesting solutions to the generalized Burger's equation.
Exactly. In example 1, it uses a specific set of coordinates. They're denoted as eta. And these represent the arc length of geodesics in the hyperbolic half-plane. Think of geodesics as the straightest paths in this curved space.
Okay, so instead of our usual x and y coordinates, we've got this e coordinate, which already tells us we're in a whole different kind of geometry here.
Right. And in this hyperbolic setting, the paper defines the spatial operator in as sin in pi times the partial derivative with respect to hang.
All right, let's break that down a bit. The sin part, that's a hyperbolic function, kind of like a hyperbolic cousin of, our regular trig functions like sine and cosine. And the partial derivative with respect to, well, that's just a fancy way of saying how much a function changes as we move along that syntect.
Right. So uni is basically measuring how a function varies along these geodesic paths in the hyperbolic half-plane. It's capturing those spatial variations, but in the context of this curved geometry.
And then there's the time operator, ot, which is just the partial derivative with respect to time. That one's pretty straightforward. It just measures how a function changes as time goes by.
Now, the paper takes these operators, right, and it defines a specific form of the generalized Burger's equation. And it's tailored to the hyperbolic half-plane. You can see it in equation 2.18 in the paper. It might look a little intimidating at first, but it's basically saying that the change in our function over time is affected by its variation along those geodesic paths, which is captured by the ni operator, and also by a term that involves the function u squared.
So we've got these spatial variations from ni interacting with this nonlinear term with a squared. And all of that's driving how the function changes over time. It's a pretty complex interplay of factors.
It is. And to make things even more interesting, the paper introduces this function, at. It only depends on time, and it acts like a scaling factor for these different terms in the equation. And at, it's chosen so that it satisfies a specific condition, namely that its derivative with respect to time is equal to minus at squared.
Okay, so at isn't just some random function. It's picked for a specific reason, to play a specific role in the equation, like a finely tuned knob that controls how these different forces balance out as the system changes over time.
Precisely. And with this setup, the paper goes on to find a solution to this generalized Burger's equation. And they use a really clever combination of techniques. One of the key tools is this transformation, at times the integral from pi zeros to ea mio st semi sds.
Wow, that's quite a mouthful. Can we unpack that a little bit?
Of course. So the exponents part, that means we're dealing with an exponential function. Those pop up all the time when you're solving differential equations. And inside the exponential, we have this integral from pi 0 to a of ust sin sds.
Okay, so that integral, it seems like it's adding up the contributions of the function ust along a geodesic path from some starting point 0 to our current point st. And I'm guessing that the first Vin factor that's there to account for the curvature of the hyperbolic half-plane.
You got it. This transformation, it's essentially making a weighted average of the function along a geodesic path. And the weights are adjusted to account for the for the hyperbolic geometry. It's like taking a snapshot of how you behaves along this path.
And what's so cool about this transformation I'm starting to see is that it makes the generalized Burger's equation a lot simpler.
Exactly. If you substitute this expression for into the equation and use some calculus tricks, the paper shows that Harris satisfies a much simpler equation. It's called the heat equation.
Ah, the heat equation. We talked about that earlier. It describes how heat flows in a material over time. And it has well-known solutions that use those Hermite polynomials.
Precisely. By turning the generalized Burger's equation into the heat equation, the paper can use those known solutions to find a solution for the original equation. It's a great example of how mathematical transformations can be used to solve really complex problems. You just map them onto simpler ones that, that we already understand.
So they're taking this complex fluid flow problem in the hyperbolic half-plane, and they're mapping it onto a heat flow problem, which they then solve using Hermite polynomials. It's like translating, I don't know, a foreign language into one they're fluent in.
That's a great way to put it. And the specific solution they find for you, it's given in equation 2.20 in the paper. It has derivatives of logarithms and Hermite polynomials. But it's a concrete example of how the generalized Burger's equation can be solved in this non-Euclidean setting.
And this is just one example. Out of many in the paper, they go on to explore other scenarios using different operators and transformations to find solutions in different contexts. It's like they're giving us a whole toolbox, of mathematical techniques for tackling these generalized Burger's equations.
And what's even more exciting is that these equations, they could potentially describe so many real-world phenomena.
Yeah.
By generalizing the Burger's equation and looking at its solutions in different geometries, the paper opens up like whole new ways of understanding things. Fluid dynamics, cosmology, maybe even other fields where, complex systems change over time.
It's wild to think we started with a pretty simple equation about traffic flow, and now we're talking about hyperbolic geometry and Hermite polynomials. What's next on our deep dive? All right, welcome back. So we've gone through a lot, from those traffic jams to that crazy hyperbolic half plane. I think now it's time to try to connect everything and see what really mind-bending stuff this paper has in store for us.
It's amazing how this paper brings together these different areas, math and physics. We saw how the generalized Burger's equation can be used for fluid dynamics, of course, but it also ties into things like Brownian motion, which you usually think of as random,
Yeah.
probability and all that.
Yeah, that Brownian motion connection was definitely a surprise. Example 3 showed how the solution to one specific version of the generalized Burger's equation in the hyperbolic half plane could be linked to, like, how particles move randomly in a fluid.
Yeah, it's a really interesting link because it suggests that maybe even these random chaotic processes like Brownian motion could be connected to, deterministic equations like the generalized Burger's equation. It's like finding some hidden order in all the randomness of the universe.
It's like, I don't know, saying that the way dust particles dance in a beam of light could be described by the same equation that governs the swirling patterns of a hurricane.
That's a great way to put it. And the key to that connection, it's in equation 2.24. It links the generalized Burger's equation to the hyperbolic Laplacian. That Laplacian, it's a mathematical operator. It measures how things spread out or diffuse in a space. But here, we're talking about that diffusion, but in the hyperbolic half plane, that weird geometry where our normal ideas about space and distance, well, they kind of break down.
So it's like saying the way a fluid flows in that strange non-Euclidean world, it's connected to how things spread out in that same space.
Exactly. And this Brownian motion connection, it shows how these generalized Burger's equations could be used to model, all sorts of things, not just regular fluid dynamics. We could be talking about finance, where Brownian motion's used for, like, stock prices, or even biology, how molecules move in a cell.
Wow, it sounds like the possibilities are endless.
And the paper keeps going. It takes things even further. It starts exploring multidimensional generalizations of the Burger's equation. Now we're not just looking at fluid flow in a line or a plane. We're in, like, full 3D space, or even higher dimensions.
Equation 4.1. That's where it all happens, this multidimensional stuff. It's a complex equation, but it lets us describe much more complicated things like, I don't know, how heat flows in a solid object, or how particles move in a magnetic field.
And example 8, it's a great illustration of how these multidimensional generalizations actually work. It uses the whole hyperbolic Laplacian thing to solve a more, intricate version of the generalized Burger's equation.
It's like taking the heat equation, the one about heat flow in a solid, and then giving it, like, this hyperbolic twist.
Exactly. And now that we can handle these multidimensional problems, well, it opens up a ton of new applications. I mean, imagine modeling, like, how air flows in the atmosphere, or how crowds move in a city, or even how a virus spreads through a population.
Okay, so for the grand finale, let's talk about black holes and curved spacetime. Example 9 takes us on this wild ride through Einstein's general relativity.
Yeah, so the Schwarzschild metric, it's in equation 4.21. It describes how space-time warps, around a massive object like a black hole. It's a mind-blowing concept where time slows down and space stretches out as you get closer to the black hole's event horizon.
It's like trying to imagine, I don't know, a universe where reality itself is, like, distorted.
And the paper actually combines this crazy metric with the generalized Burger's equation. It's in equation 4.25. It's like we're trying to describe how a fluid flows, but in a universe where space and time work totally different from our everyday experience.
And they actually found a solution for that.
They did. Equation 4.29. It's a solution to the generalized Burger's equation in this warped space-time. It really shows you how powerful math can be to describe even the most extreme and bizarre stuff in the universe.
And then there's the cigar soliton, that strange, beautiful solution to the Ricci-flow equation, the one that describes how the geometry of space can change over time, like a cosmic cigar that stretches and shrinks but keeps its overall shape.
Yeah, equation 4.31, that's the essence of that cigar-Salton metric. And the paper actually finds a solution to the generalized Burger's equation in this dynamic spacetime, too. It's in equation 4.34.
It's a reminder that even in the vastness of space, there can be these hidden patterns and order.
So we started with basic fluid dynamics, and we ended up in the warped space-time of black holes and a universe that's constantly changing. It's been a wild ride exploring the power of the generalized Burger's equation.
This whole deep dive has really opened my eyes to all these new mathematical possibilities. It makes you wonder, and want to explore more.
And that's the best part. This journey, it's just the beginning. Who knows what other connections and applications are out there, hidden in these equations, waiting for someone to discover them.
Yeah, to everyone listening, we hope this makes you think and go explore those mysteries of the universe, With everything we've talked about today, maybe you'll be the one to make that next big discovery. Thanks for joining us on this deep dive.